America's biggest construction megaprojects are reaching completion in 2026 and redefining what large-scale building can achieve. From massive transportation corridors to cutting-edge industrial hubs, these projects represent years of planning, billions in investment, and some of the most complex engineering ever attempted. Today, we uncover the megaprojects finishing in 2026 and what their completion means for the future of the United States. Towering cranes and steel skeletons have come to define the skyline around Nashville International Airport, where the BNA Vision project is unfolding as a multi-phase transformation of terminal infrastructure, passenger amenities, and operational capacity. This sweeping development plan is designed to accommodate explosive regional growth and rising air travel demand. As part of this ongoing program, by 2026, several major components will reach full completion, including expanded concourses, a new on-airport hotel, and integrated ground transportation facilities, all aimed at redefining the traveler experience while future-proofing the airport's functionality. Central to the effort is the construction of a new terminal lobby and ticketing hall expansion, which involves reconfiguring the central terminal core with additional vertical space, new structural framing, and large-span roof trusses. This lobby incorporates high-performance glazing systems for natural light, post-tensioned concrete slabs for uninterrupted floor plates, and advanced mechanical systems to handle the increased foot traffic. The new hall connects seamlessly to both the south and north concourses, forming a unified passenger circulation loop. One of the largest structural packages nearing completion by 2026 is the satellite concourse expansion. Built with steel framing and deep foundation systems, the expanded concourse adds dozens of new gates equipped with modern boarding bridges, energy-efficient HVAC systems, and wide passenger hold rooms. Each gate is supported by a modular utility backbone that includes data cabling, potable water, and baggage handling extensions. The floor assembly utilizes composite steel decking with concrete topping slabs, designed to support both passenger loads and integrated seating, charging stations, and wayfinding systems. Adjacent to the terminal is the new hotel development, a significant vertical addition to the campus. This high-rise structure is built using reinforced concrete cores and shear walls to provide lateral stability against wind and seismic forces. The hotel, which is on schedule for full interior completion by 2026, is directly connected to the terminal via a covered pedestrian bridge and includes amenities such as conference rooms, restaurants, and observation decks overlooking the airfield. Mechanical plant systems are located on rooftop penthouses, concealed by architectural screening, and are supported by a network of steel beams and slab-on-metal deck construction. On the airside, airfield reconfiguration and apron expansions are underway to support the added gate capacity. This includes new concrete paving slabs poured in large contiguous sections with dowel baskets, expansion joints, and embedded lighting. Jet fuel hydrant systems are integrated beneath the apron surface, supported by trench access points and utility vaults. Stormwater runoff is controlled by a series of trench drains and retention basins designed to meet FAA environmental compliance standards. Ground transportation infrastructure is also being upgraded as part of the BNA Vision, with new roadways, parking garages, and shuttle facilities. These structures are built using precast concrete panels and post-tension beams for fast-track assembly. Intelligent transportation systems are embedded into the structure, with real-time occupancy sensors, automated ticketing systems, and dynamic signage. The Darien Metro North Station renovation in Connecticut is a transformative infrastructure project aimed at modernizing one of the busiest commuter hubs of the state. Situated on the New Haven line, this station serves as a major link between New York City and coastal Connecticut, catering to over 2,000 commuters daily. Originally built in the early 1900s, the aging platforms of the station outdated facilities, and non-compliant design had long made it a bottleneck in the rail network. The project was launched to transform the station into a safe, accessible, and modern transit hub. The initial budget of $34 million was later revised to $40 million, primarily due to unforeseen underground utility conflicts and structural deficiencies discovered during early demolition. The decision was made to adopt modular construction techniques and increase night shift activity to compensate for lost time. These efforts paid off. The station is all set to complete around March 2026, meeting all federal safety and accessibility standards. The renovation includes a complete rebuild of both inbound and outbound platforms, extended to accommodate 10-car trains. Platforms were replaced using prefabricated concrete sections, allowing installation to proceed rapidly with minimal daytime service interruptions. New high-intensity LED lighting was installed across the site to enhance visibility and deter crime, especially during early morning and evening commutes. These lights were integrated with motion sensors to reduce energy consumption during low traffic periods. In terms of accessibility, the overhaul was a game changer. The station is now fully ADA compliant, with 2 new high-capacity elevators, wider ramps, tactile warning strips along platform edges, and visual audio announcement systems. Boarding trains are now faster and safer, especially for seniors and people with disabilities. Commuter comfort was also a major focus. The platforms are now covered by curved steel frame canopies with built-in heaters to provide shelter in cold or rainy conditions. Waiting areas include digital train schedules, real-time delay notifications, Wi-Fi access, and retail kiosks, turning the station into a functional waiting space rather than just a transit point. From a construction technology perspective, the project leveraged GPS-guided track alignment systems and vibration monitoring equipment to protect nearby structures from potential damage during foundation work. Electric mini excavators were used during night shifts to reduce noise in the residential zone, and hydraulic slab lifters helped place prefabricated segments with millimeter accuracy. By the time of completion, the Darien Metro North Station had become more than just a renovated stop. It had evolved into a model for sustainable, user-friendly, and future-ready rail infrastructure.
In 2026, right in the heart of San Francisco's Soma district, the 5M project stands as one of the city's most active megaprojects under construction. This mixed-use development is bringing new energy and density to the blocks surrounding Mission, 5th, and Howard Streets. Long a patchwork of surface lots and low-rise structures, designed to create a live work-play ecosystem in the center of downtown. The 5M project is pushing forward this year with the final phases of its build-out, aiming for full completion by 2027. The core of the project is a multi-building, multi-acre redevelopment that includes housing, office space, community facilities, and public plazas. As of 2026, the residential component is nearing its final stages, with interiors being completed, amenity spaces outfitted, and streetscape work wrapping up. One of the tallest residential towers in the project, now visibly finished on the exterior, is expected to open its doors by early 2027, offering a mix of market rate and affordable units, over 300 in total. The office and commercial buildings that anchor the project are also active hubs of construction. Fit-outs are progressing in multiple towers, preparing space for tech, nonprofit, and creative sector tenants. In 2026, these buildings are expected to start welcoming their first occupants by the end of the year, with full occupancy likely achieved in 2027. It's part of a broader shift in the area, as Soma continues to re-establish itself not just as a tech district, but as a vibrant, mixed-use downtown core. What sets 5M apart in the landscape of San Francisco's 2026 megaprojects is its emphasis on integration with the community. More than just a real estate development, the project was designed to create active public space and cultural infrastructure. At the center of the site, the 5M Park, currently under construction, is being landscaped with flexible gathering areas, art installations, and play zones for families. This green space is scheduled to open alongside the residential buildings in mid-2027 and is expected to become a crucial urban amenity for residents, workers, and visitors alike. This year, the construction crews are focused not only on completing vertical structures, but also on activating the ground plane. Sidewalks are being widened, bike infrastructure is going in, and retail storefronts are being prepped for future cafes, shops, and local businesses. The aim in 2026 is to finish creating a neighborhood that doesn't shut down after office hours, a place where people live, work, eat, and gather 7 days a week. One of the most significant elements under construction now is the dedicated nonprofit office hub and arts space, which will house multiple local organizations and creative initiatives. This facility is central to the 5M vision, supporting equity, inclusion, and community-based growth in a rapidly evolving part of the city. Completion is on track for late 2026, with programming expected to launch shortly after. From a development standpoint, the 5M project is compact compared to some of the sprawling waterfront megaprojects elsewhere in San Francisco. But in 2026, it punches far above its weight in terms of impact. Located just blocks from Powell Street BART and Muni lines, its density and transit connectivity make it a model of sustainable urban development, and its blend of housing, employment, and civic use is already influencing how other central city projects are being designed.
South of Dallas's central business district, the K. Bailey Hutchison Convention Center is undergoing a comprehensive expansion and reconstruction that places it among the most consequential megaprojects under construction in the city in 2026. The project is not a simple addition to the existing facility, but a phased redevelopment designed to modernize one of the largest convention centers in the region while maintaining event operations throughout construction. The expansion replaces large portions of the aging convention center with new structures that significantly increase usable exhibition space, improve circulation, and align the facility with current national convention standards. The redevelopment is also closely tied to downtown Dallas's broader urban strategy, including connectivity to surrounding districts and preparation for major international events. By 2026, the project is in its most intensive construction phase. Demolition of outdated exhibition halls and support spaces has largely been completed, allowing new structural work to dominate the site. Crews are actively engaged in deep foundation construction, including drilled piers and mat foundations designed to support long-span exhibit halls and multi-level meeting facilities. These foundations are engineered to accommodate heavy floor loads associated with large conventions and trade shows. Superstructure construction accelerates throughout 2026. Steel framing for expansive exhibit halls is erected using long-span trusses that minimize interior columns and maximize flexible floor space. Concrete cores housing vertical circulation, mechanical shafts, and life safety systems rise concurrently. The sequencing of this work is carefully planned to allow portions of the existing convention center to remain operational while new sections are built adjacent to them. Exterior enclosure becomes a major focus during 2026. Crews install curtain wall systems, precast panels, and roofing assemblies as structural work reaches completion in phases. These systems are designed for durability, energy efficiency, and acoustic performance, reducing operational costs and improving the experience for both exhibitors and visitors. Interior construction advances rapidly in 2026 across completed structural zones. Mechanical, electrical, and plumbing systems are installed to support modern convention requirements, including high-capacity power distribution, advanced HVAC systems, and extensive data infrastructure. These systems are designed to accommodate simultaneous large events with high technology demands, such as trade shows requiring heavy electrical loads and extensive connectivity. Circulation and access improvements are a critical component of the 2026 construction scope. New concourses, meeting room clusters, and pre-function spaces are being built to improve wayfinding and reduce congestion. Vertical transportation systems, including escalators and elevators, are installed to efficiently move large crowds between exhibit levels and meeting spaces. These improvements address long-standing operational limitations of the original facility. Site and infrastructure work continues alongside vertical construction in 2026. Roadway realignments, service access improvements, and utility upgrades are underway to support increased event traffic and logistics operations. Stormwater management systems are being upgraded to meet current standards and reduce flood risk in a historically vulnerable area of downtown. From a scheduling perspective, 2026 represents a midpoint to late middle stage of the overall redevelopment timeline. Major structural elements of the new expansion are expected to be completed during this period, with enclosure and interior build-outs extending into subsequent years. Phased openings allow new sections of the convention center to come online while construction continues elsewhere on the site. In the expanse of the Texas Panhandle, the Sanford Dam plays a pivotal role in regional water management and flood control, particularly as it impounds Lake Meredith on the Canadian River. Originally constructed in the early 1960s, the dam was designed as an earth-fill embankment with a concrete spillway, serving the dual purposes of municipal water supply and mitigating downstream flooding. Over time, the infrastructure aged, prompting a phased rehabilitation effort aimed at enhancing safety, structural resilience, and operational efficiency. By 2026, significant structural upgrades and instrumentation installations are scheduled for completion, focusing on both the dam body and the outlet work system. One of the central aspects of the modernization program involves strengthening the earthen embankment, which spans nearly 7,000 feet in length and rises over 100 feet above the original riverbed. Crews began by performing extensive geotechnical investigations, including borehole sampling and soil stability analysis, to identify zones of potential seepage or differential settlement. Based on these findings, filter and drain systems were redesigned. A new chimney filter composed of well-graded sand and gravel was installed internally, sandwiched between impermeable clay cores and the outer embankment shell. This redesign allows any infiltrating water to be safely collected and discharged, significantly reducing the risk of piping failure. The downstream slope was regraded and armored with riprap composed of heavy angular rock to guard against erosion from rainfall and potential overtopping. In conjunction with this, tow drains and relief wells were refurbished or newly constructed to relieve hydrostatic pressure and to provide observable points of seepage monitoring. Construction sequencing was carefully managed to maintain reservoir capacity and dam integrity, with earth-moving equipment operating in staged zones and GPS-controlled graders ensuring design specifications were met. The spillway system, originally cast in reinforced concrete and located near the left abutment, underwent its own set of enhancements. Cracking and scaling on the spillway crest and chute surfaces were repaired using epoxy injection and shotcrete overlay techniques. Expansion joints were replaced with water stops designed to accommodate thermal movement while maintaining water tightness. New aerators were installed within the chute profile to minimize cavitation damage under high flow conditions. The stilling basin at the spillway's toe was also restructured with improved energy dissipation blocks and reinforced apron slabs. Another major element reaching completion by 2026 is the modernization of the outlet works. The original gated conduits and control valves were replaced with stainless steel slide gates operated by hydraulic actuators housed within a new gate chamber structure. This upgrade improves flow regulation, allowing more precise water delivery to downstream users. New access galleries were constructed for maintenance and inspection, and redundant power supply lines were routed to ensure system operability during electrical outages. A comprehensive instrumentation network was added throughout the dam structure and appurtenant works. Vibrating wire piezometers, inclinometers, and settlement plates were embedded at key points to monitor pore pressure, movement, and subsurface changes in real time. These data feeds are linked to a centralized supervisory control and data acquisition system, which supports predictive maintenance and emergency response planning. Let's travel over to Chicago, Illinois, where the O'Hare 21 terminal expansion is redefining the future of air travel in the United States. Being one of the busiest national airports, O'Hare International Airport is undergoing a transformative $8.5 billion modernization initiative, with the Terminal 5 expansion serving as a pivotal component. The expansion of Terminal 5 is designed to address the increasing demand for both domestic and international air travel. By enhancing capacity and integrating state-of-the-art facilities, the project aims to improve passenger experience, operational efficiency, and maintain the status of O'Hare as a global aviation hub. Completed in early 2023, the Terminal 5 expansion added approximately 350,000 square feet to the existing structure, increasing the capacity of the terminal by 25%. This expansion includes 10 new gates, 9 of which utilize multiple aircraft ramp system gates, allowing flexibility to accommodate both wide-body and narrow-body aircraft. The project also involved the renovation of 750,000 square feet of existing space, enhancing passenger amenities by 75%. Key improvements include a reconfigured international arrivals facility, expanded customs and security checkpoints, and a complete overhaul of the baggage handling system. With a total investment of $1.3 billion, the Terminal 5 expansion is part of the broader O'Hare 21 program. This modernization effort is expected to generate substantial economic benefits, including job creation during construction and increased capacity to support future air traffic growth. The project employed advanced construction techniques to minimize disruptions and enhance sustainability. Notably, the design incorporates 40,000 square feet of high-performance glass, water-efficient fixtures exceeding sustainable airport manual requirements, and new Energy Star roofing. The vaulted ceilings and open design of the terminal allow natural light to permeate the space, reducing energy consumption and creating a welcoming environment for travelers. In addition to structural enhancements, the Terminal 5 expansion includes a significant cultural investment. A $3.5 million public art program, the largest single acquisition of works by local artists in Chicago in 30 years, features installations throughout the terminal. These artworks celebrate the diverse communities of the city and provide travelers with an enriched cultural experience. Furthermore, a new 6-story parking garage is under construction, set to open in October 2025. This facility will more than double the available parking at Terminal 5, accommodating the anticipated increase in passenger volume.
In 2026, one of the most visually dramatic megaprojects under construction in San Francisco is the redevelopment of the Potrero power station site. Rising on a stretch of industrial waterfront in the Dogpatch neighborhood, this 29-acre site is being transformed from a rusting relic of the city's energy past into a dense, mixed-use community that blends housing, innovation space, and public waterfront access. After decades of inactivity and pollution, the area is now filled with active construction. with multiple buildings rising around the preserved smokestack that once powered large parts of San Francisco. This year marks a turning point in the project's timeline. Key infrastructure has been installed, roads are taking shape, and vertical construction is advancing on several residential and commercial buildings. The first wave of occupancy is expected in 2027, while full build-out of the project will continue into the early to mid-2030s. In terms of current construction activity, 2026 is the first year where the scale and form of the new neighborhood are clearly emerging on the skyline. The development plan includes over 2,600 residential units, 20% of which are designated as affordable, along with office space, labs, retail, cultural venues, and a massive new waterfront park. In 2026, at least 4 parcels are under active construction, with cranes on site, facades being installed, and streetscape work underway to connect the site to the surrounding Dogpatch and Pier 70 developments. The power station's original brick boiler house is being stabilized and preserved to eventually be converted into a centerpiece public building, part of a broader trend in the project to mix new construction with industrial heritage. The Potrero power station site has long been one of the last undeveloped pieces of San Francisco's southeastern waterfront, and in 2026, it's becoming a key node in a chain of megaprojects that are physically reconnecting the city to its shoreline. The public realm is a major focus of the construction, with waterfront promenades, plazas, and parks currently being graded and landscaped to open in stages beginning in 2028. These green spaces are designed not just for beauty, but for resilience, integrated with sea level rise protection and sustainable stormwater systems. A major portion of the site is also being prepared for future commercial tenants in the life sciences and advanced technology sectors. In 2026, lab-ready office space is under construction, with leasing expected to begin the following year. These facilities are a core part of the megaproject's economic impact, offering high-tech employment opportunities and reinforcing San Francisco's role in the Bay Area Innovation Corridor. Construction in 2026 is being carried out with strict environmental oversight, given the site's legacy as a fossil fuel power plant. Soil remediation, groundwater treatment, and air quality monitoring are ongoing as each new section of the site is prepared for development. This adds complexity, but also makes the transformation more significant, turning a brownfield into a 21st century neighborhood that meets the city's housing and sustainability goals. When fully completed, the Potrero Power Station will be a dense, transit-rich waterfront extension of the city, blending over 6 acres of parks, thousands of homes, and over 1 million square feet of office and retail space into a single cohesive community. In the landscape of San Francisco's 2026 megaprojects, it stands out for its mix of industrial past and future potential. Every structure rising here is part of a deliberate effort to reshape how cities evolve, from polluted infrastructure into vibrant, livable places.
Set slightly apart from the historic core of downtown Dallas, the Bank of America Tower at Parkside represents one of the most prominent vertical megaprojects under construction in the Dallas region in 2026. Rising within the Park District near Clyde Warren Park, the tower is positioned as a next-generation commercial office building designed to consolidate major corporate operations while redefining the northern edge of the central business district. The project consists of a high-rise office tower with a large floor plate, advanced building systems, and integrated public realm improvements. It is designed to accommodate a single major anchor tenant while also supporting multi-tenant flexibility. The structure replaces older, lower-density development, reflecting a shift toward taller, more efficient office buildings in Dallas's core employment zones. By 2026, the Bank of America Tower at Parkside is firmly in its vertical construction phase. Structural framing dominates activity throughout the year, with reinforced concrete cores and post-tensioned floor slabs rising steadily above street level. Tower cranes remain on site through most of 2026 to support formwork, rebar placement, and concrete pours as the building progresses floor by floor. Facade installation becomes a major focus during 2026. Curtain wall systems, consisting of high-performance glass and metal panels, are installed from the lower levels upward as the structure tops out. This work is carefully sequenced with interior construction to allow mechanical and electrical rough-ins to follow closely behind the enclosure of each completed floor. The facade is engineered for solar performance, glare reduction, and long-term energy efficiency. Interior construction accelerates significantly during 2026. Mechanical, electrical, and plumbing systems are installed across multiple levels simultaneously. This includes high-capacity HVAC systems designed for dense office occupancy, advanced air filtration, and smart building controls. Electrical infrastructure includes redundant power distribution and backup systems consistent with large financial and corporate tenants. Elevator installation is another critical task, underway in 2026. High-speed elevator shafts are completed within the concrete core, followed by cab installation, guide rails, and control systems. These systems are designed to minimize wait times while serving a tall structure with large floor plates and high daily occupancy. Ground-level construction remains active throughout 2026 as well. The tower integrates structured parking, loading docks, and secure service access beneath and adjacent to the building. Streetscape improvements, including widened sidewalks, landscaping, and pedestrian connections to nearby parks and transit routes, are constructed alongside vertical progress. These elements are coordinated with city infrastructure upgrades to minimize disruption in a dense urban environment. Life safety systems are installed and tested in phases during 2026. Fireproofing, sprinkler systems, smoke control, and emergency power infrastructure are integrated as each floor reaches substantial completion. These systems must be commissioned incrementally to support ongoing construction above occupied or enclosed levels. From a scheduling perspective, 2026 represents the midpoint to late middle phase of the project timeline. Structural topping out is expected either during or shortly after 2026, depending on sequencing and weather conditions. Once the structure is complete, focus shifts more heavily toward interior finishes, tenant build-outs, and systems commissioning. Major construction activity continues into 2027, with interior finishes, lobby construction, exterior plaza completion, and final facade detailing extending well beyond the structural phase. Testing and commissioning of building systems, including elevators, HVAC, and security systems, are expected to continue through late 2027. Set in the rolling terrain of Fannin County, Texas, the Leonhurst Dam is a key feature in the development of Lake Ralph Hall, a major water supply reservoir under construction to meet the growing demands of the North Texas region. This dam is a crucial component of a broader infrastructure program designed to provide long-term water reliability while incorporating environmental and recreational benefits. The project includes an earthen embankment dam, intake and outlet structures, spillways, and various support facilities. By 2026, the dam embankment, outlet works, and much of the lake basin clearing and impoundment control systems are scheduled for completion, representing the functional establishment of the reservoir. The dam itself is a zoned earthfill embankment, meaning it is constructed using distinct layers of different soil materials, each selected for specific geotechnical properties. The central core is composed of low permeability clay, forming an impermeable barrier to prevent seepage. This core is flanked by progressively more permeable materials: sand, gravel, and rock that provide both structural support and controlled drainage. These zones are compacted in thin lifts using heavy compaction equipment to achieve the necessary density and bonding between layers. Foundation preparation was one of the earliest and most critical steps in the construction process. It began with stripping of topsoil and removal of organic materials, followed by proof rolling and excavation down to suitable bearing strata. A cut-off trench was excavated beneath the core zone and keyed into bedrock or highly consolidated clay, effectively reducing the risk of underseepage. As an added precaution, grout curtains were drilled along the alignment to seal fractures and enhance subsurface impermeability. As the embankment rose, real-time monitoring was implemented using inclinometers, piezometers, and settlement gauges. These instruments provided engineers with continuous data on pore water pressures, lateral movement, and vertical deformation, allowing timely adjustments to fill placement and moisture conditioning. The upstream slope of the dam was armored with riprap to guard against wave action and erosion once the reservoir reaches operational levels, while the downstream slope was protected with turf reinforcement and slope drains. The outlet work structure, also on track for completion by 2026, consists of a reinforced concrete intake tower, gated conduit, and stilling basin. The intake tower includes multiple inlets at different elevations, allowing selective withdrawal for optimal water quality. Flow from the intake travels through a concrete-lined tunnel beneath the dam, controlled by a series of hydraulically operated gates and valves. At the toe of the dam, flow is discharged into a stilling basin lined with energy dissipation blocks and reinforced slabs to prevent scour and erosion. Spillway construction includes a broad-crested weir and a concrete chute extending down the abutment. The spillway is designed to safely pass the probable maximum flood without overtopping the embankment. It incorporates erosion-resistant lining and aerators to minimize cavitation effects during high-velocity flow events. By 2026, the dam embankment and hydraulic structures will be fully constructed, enabling the initial stages of reservoir impoundment and system commissioning. This milestone signifies the transformation of the site from an active construction zone into a functioning regional water resource, marking a major advancement in North Texas water infrastructure. By the middle of the decade, one of North Texas's earliest soccer-specific stadiums is undergoing a comprehensive reconstruction that places it firmly among Dallas area megaprojects active in 2026. The new Toyota Stadium redevelopment in Frisco represents a multi-year modernization effort focused on structural capacity, revenue generation, climate mitigation, and long-term event flexibility rather than a simple renovation. Toyota Stadium originally opened in 2005, designed for a different era of Major League Soccer and a much smaller regional population. The redevelopment project restructures the existing stadium rather than replacing it, allowing FC Dallas to continue operations while construction advances in carefully sequenced phases. By 2026, the project is deep into its most technically demanding stage, with heavy construction occurring throughout the seating bowl, concourses, and building systems. Construction work during 2026 concentrates on major structural modifications. Entire sections of the lower bowl are being demolished and rebuilt to adjust rake angles, improve sightlines, and support additional vertical loads from new premium levels above. New concrete pours and steel framing are installed in phases to maintain stadium stability, while adjacent areas remain operational. This year also includes reinforcement of existing foundations to meet updated building codes and support heavier roof and canopy systems. One of the most visible construction efforts in 2026 is the installation of expanded canopy structures. These roof elements are designed to significantly increase shaded seating, addressing long-standing heat exposure issues. The canopy construction involves large-span steel trusses, integrated lighting mounts, and future-ready broadcast attachment points. Installation is staged section by section to allow partial stadium use during the soccer season. Premium seating and hospitality spaces dominate interior construction in 2026. New club lounges, lodge boxes, and suites are being built into previously underutilized stadium volume. This requires extensive mechanical and electrical upgrades, including new air handling units, upgraded power distribution rooms, and expanded data infrastructure. Plumbing systems are also being replaced or rerouted to serve higher capacity food and beverage operations. Concourse reconstruction is another major focus in 2026. Existing concourses are being widened, regraded, and reconfigured to improve circulation and accessibility. Vertical transportation systems, including elevators and stairs, are being added or relocated to comply with modern accessibility standards. These changes require careful coordination between demolition crews, concrete teams, and utility installers to avoid service disruptions. Technology infrastructure work accelerates during 2026. Crews are installing new fiber optic backbones, wireless access systems, and security networks throughout the stadium. Dedicated broadcast rooms and control spaces are under construction to support national and international television requirements. These systems are designed to accommodate future tournaments and non-soccer events without additional major retrofits. Outside the Stadium Bowl, 2026 construction includes the redevelopment of surrounding plazas and entry zones. Pedestrian circulation is being improved through expanded hardscape areas, upgraded lighting, and reworked security screening layouts. These exterior improvements are engineered to support higher peak attendance and year-round events, not just match days. Sustainability measures are integrated into the 2026 construction scope. Lighting systems are being converted to high-efficiency LED fixtures. Water infrastructure is upgraded with low-flow systems, and stormwater management improvements are installed to reduce runoff during heavy rain events. Older materials removed during demolition are being recycled or reused where feasible to reduce construction waste. From a timeline perspective, 2026 represents the midpoint of the redevelopment. Structural and exterior envelope work dominates early and mid-year, while interior build-outs continue into late 2026 and beyond. Some premium areas and upgraded seating sections are expected to open in phases as construction completes, allowing incremental increases in stadium functionality. Major construction activity is scheduled to continue through 2027, with final interior finishes, technology commissioning, and operational testing extending into late 2027. Full project completion is expected between late 2027 and 2028, depending on seasonal construction constraints and event scheduling. The phased delivery approach ensures continuous stadium use while transitioning the facility to its final configuration.
The Mission Rock project is one of San Francisco's headline megaprojects under active construction in 2026. Sitting directly south of Oracle Park, on what was once a windswept sea of asphalt and overflow parking lots, this 28-acre waterfront site is being turned into a dense, walkable neighborhood that combines housing, parks, offices, and retail in one of the most high-profile real estate efforts in the city. In 2026, the project is deep in Phase 1 construction. Several major buildings have already topped out, with exterior work wrapping up and interior build-outs ongoing. Full completion of this phase is expected by late 2027. When finished, it will include nearly 1,200 new residential units, over 400 of which are permanently affordable, along with 8 acres of new public space and over 200,000 square feet of office and retail space. This megaproject isn't just reshaping a site, It's helping to redefine the southern edge of San Francisco's downtown. New streets and pedestrian promenades are already being laid out, stitched together by green infrastructure and open-air plazas designed to absorb stormwater and resist sea level rise. The waterfront park, known as China Basin Park, is being built in tandem with the buildings around it. Crews in 2026 are currently sculpting the park's shoreline and planting native vegetation, with major portions set to open by 2028. Mission Rock is a public-private partnership between the San Francisco Giants and the Port of San Francisco, and the construction in 2026 reflects a long-term vision to extend the city's core outward along the waterfront. Designed as a high-density, low-emissions community, every new structure is being built to LEED Gold or higher standards. Solar panels, all-electric systems, and smart energy grids are standard here, not just features. One of the project's architectural landmarks now under construction is the Canyon, a massive mixed-use building that blends market-rate apartments with carved terraces and retail space. In 2026, the Canyon's facade is nearly complete, and interior work is progressing toward a mid-2027 delivery. Nearby, a life sciences tower being built for the biotech sector is rising quickly, with tenants expected to begin occupancy by late 2028. What makes Mission Rock such a key part of San Francisco's 2026 megaproject landscape is its fusion of uses and its central location. Unlike isolated developments on the city's edges, this project plugs directly into the transit network and urban fabric. It's within walking distance of downtown, BART, Caltrain, and multiple Muni lines. Its completion will not only provide urgently needed housing, it will expand the city's job base and public amenities in a place long dominated by underused land. As of 2026, the construction site is a hive of activity. Steel framing, glazing, mechanical installation, and hardscape development are all occurring simultaneously across multiple parcels. Each building is being developed by a different architectural team, resulting in a diversity of forms and styles that break from the monolithic look of some other megaprojects. This is intentional. Mission Rock is designed to feel like a neighborhood, not a master plan. The entire project is expected to wrap up in multiple phases through the early 2030s, with new parcels starting construction as others finish. By the time it's fully built out, Mission Rock will include 8 acres of parks, up to 1.4 million square feet of commercial space, and space for thousands of new residents.
Stretching across agricultural fields and transportation corridors in California's Central Valley, the Hanford Viaduct is one of the most prominent elevated structures in the state's high-speed rail program. Designed to carry future high-speed trains over highways, irrigation canals, and local roads, this viaduct exemplifies long-span bridge engineering on a linear infrastructure scale. Extending more than 6,000 feet in length, the structure is a major part of the route connecting the cities of Bakersfield and Merced. By 2026, substantial portions of the viaduct's superstructure and supporting piers are scheduled for full completion, marking a key advancement in California's effort to build the nation's first dedicated high-speed rail system. Construction began with foundation work on deep pile supports, essential for distributing loads through the soft valley soils and into more stable substrata. Each pile cap anchors groups of cast-in drilled hole piles, some reaching depths of over 100 feet. These piles were installed using large rotary drilling rigs, followed by steel cage placement and concrete pours using tremie methods to avoid soil intrusion. Reinforced pile caps were then formed and cast to support vertical columns rising in pre-engineered intervals along the structure's path. The viaduct's columns are typically cast in place, reinforced concrete shafts with integrated rebar cages designed to resist bending and shear forces from seismic events. Column heights vary based on topography and the elevation required to clear existing obstacles, such as State Route 198 and other major infrastructure. Formwork systems were employed in a climbing sequence, allowing successive concrete pours to build up each column in increments. Once cured and post-tensioned, these columns were capped with pier tables, forming the intermediate support points for the superstructure. The superstructure itself consists of precast concrete girders installed using balanced cantilever construction techniques. Segments were fabricated at a dedicated casting yard, then transported to the site via specialized haulers. Large capacity cranes and launching gantries were used to lift and position these segments atop pier caps, where they were aligned and post-tensioned together with steel cables. This method minimized on-site curing time and allowed for faster assembly across long spans without requiring extensive scaffolding or temporary shoring in active roadways or sensitive environmental zones. Bridge deck construction followed closely behind girder placement. Deck slabs were cast in place atop the precast segments using slip-form paving machines and high-strength concrete mixers designed for thermal resistance and structural integrity. Expansion joints, shear connectors, and deck drainage features were integrated into the pour sequence. Parapet walls and safety barriers were cast with embedded conduit for future rail electrification and signaling systems. By 2026, the entire structural assembly of the Hanford viaduct, including all columns, girders, and deck sections, is expected to be completed, enabling future track installation and system outfitting. This milestone signals the transition from heavy civil construction to rail-specific phases such as ballastless track slab installation, overhead contact system erection, and control system integration. At the center of North Texas's expanding regional rail network, the Dart Silver Line stands as one of the most complex transportation megaprojects under construction in the Dallas region in 2026. Unlike traditional light rail lines, the Silver Line is being delivered as a commuter-style corridor designed to connect suburban employment centers, major airports, and existing rail systems across multiple cities in Collin, Dallas, and Tarrant counties. The Silver Line is a roughly 26-mile east-west rail corridor stretching from Shiloh Road in Plano to DFW Airport North Station. It repurposes and upgrades an existing freight rail right-of-way, requiring extensive coordination between passenger rail construction and ongoing freight operations. This shared corridor condition defines much of the construction activity occurring in 2026, making the project significantly more complex than greenfield rail lines. By 2026, the Silver Line is firmly in its peak construction phase. Track installation and rehabilitation are ongoing across multiple segments, including full replacement of rail, ties, ballast, and drainage systems to meet passenger rail standards. In several areas, parallel tracks are being added or extended to allow freight and passenger trains to operate simultaneously without service conflicts. These works require nighttime construction windows and precise scheduling to minimize disruption. Station construction is a major focus during 2026. All planned stations serving Plano, Addison, Carrollton, Capel, and DFW Airport are in various stages of vertical construction. Platform structures, canopies, elevators, stairways, and pedestrian bridges are being built concurrently at different sites. In 2026, crews are installing structural steel, pouring elevated platforms, and beginning architectural finishes at stations that reached foundation completion in earlier years. Grade crossing reconstruction defines another major category of 2026 construction. Dozens of roadway crossings along the corridor are being rebuilt or upgraded with new signaling systems, gates, medians, and roadway geometry. Some crossings are being closed or consolidated entirely to improve safety and reduce long-term maintenance. These works require coordination with local municipalities and involve phased traffic shifts that extend throughout the year. Bridge and structure work continues through 2026 at multiple locations. Existing rail bridges are being widened, reinforced, or replaced to support increased rail traffic and modern load requirements. In flood-prone areas, embankments and culverts are being rebuilt to improve resilience against extreme weather events. These civil works represent some of the most capital-intensive portions of the project. Systems installation accelerates significantly during 2026. Crews are deploying signaling and train control systems designed for higher speed regional rail service. This includes centralized traffic control infrastructure, communication systems, and safety monitoring equipment. Fiber optic networks are being installed along the corridor to support real-time operations, dispatching, and passenger information systems. From a timeline perspective, 2026 is a transition year between heavy civil construction and operational readiness. While earthwork and major structures dominate early phases of the project, 2026 sees a shift towards systems integration, station completion, and corridor-wide testing preparation. Track work and signaling installation continue into 2027, followed by extensive testing and certification. Revenue service is not expected to begin in 2026. Instead, late 2026 and 2027 are dedicated to system testing, operator training, safety certification, and coordination with freight rail partners. Full passenger service is anticipated after completion of these phases, with opening targeted in the latter part of the decade, contingent on testing and regulatory approval timelines. Within the broader context of Dallas megaprojects under construction in 2026, the DART Silver Line is distinct for its regional impact rather than visual prominence. It directly connects major job centers, suburban cities, and DFW Airport without requiring transfers through downtown Dallas. Its construction reshapes an existing rail corridor into a modern passenger system, expanding mobility options across one of the fastest growing metropolitan regions in the United States.
Candlestick Point and Hunters Point Shipyard are among the most active megaprojects in San Francisco as of 2026. Spanning more than 700 acres along the city's southeastern shoreline, this redevelopment effort is in full swing, reshaping two long-neglected sites into a new urban district. Construction is progressing across multiple parcels, with new streets, housing blocks, and parks taking shape, setting the stage for what will become one of the largest residential and commercial expansions in San Francisco's modern history. At Candlestick Point, where the old stadium was demolished years ago, heavy machinery is grading land for the first wave of residential and retail construction. Multiple mid-rise buildings are rising along a newly gridded street layout. These early phases, expected to complete between 2027 and 2029, will include thousands of homes, many designated as affordable, as well as the backbone of a future retail corridor and public transit connections. Parks and green infrastructure are being built alongside housing, integrating sea level rise protections and climate-resilient landscaping directly into the urban form. To the north, at Hunters Point Shipyard, development is further along. Phase 1 construction is already well underway, with completed townhomes and condos beginning to fill with residents. Additional parcels are actively under construction in 2026, adding new units monthly. Commercial spaces, artist studios, and civic buildings are also under development. Part of the project's goal to restore not just housing, but economic vitality to a part of the city long cut off from opportunity. When fully built out in the early 2030s, the combined Candlestick Hunters Point project will deliver over 12,000 new homes, more than 300 acres of open space, and millions of square feet of office, retail, and cultural uses. It's a complete neighborhood emerging from land that was, for decades, contaminated, fenced off, and largely abandoned. What's distinctive about this project in 2026 is its physical and social scale. This isn't a small infill development or a single commercial tower. It's a city-scale expansion happening within the city limits. Infrastructure is being laid from scratch. Power grids, sewer lines, transit loops, and broadband networks are all part of the foundational work occurring now. Major sections of waterfront are being rebuilt with ecological restoration in mind, with plans for habitat zones, walking trails, and public piers that will eventually reconnect residents with the shoreline. Affordable housing is a central element of the development, and 2026 marks a critical point as the first large wave of affordable units nears completion. These are being reserved in part for legacy residents of Bayview Hunters Point, addressing historic displacement and economic exclusion. Community input remains part of the planning process, particularly in shaping local hiring programs and cultural preservation efforts. Construction challenges remain. Environmental safety is closely monitored due to the site's naval and industrial history. Some parcels require more remediation than others, which is influencing the pace of development. But in terms of raw activity, cranes, crews, and square footage under construction, Candlestick Point and Hunters Point Shipyard rank among the most dynamic megaprojects in San Francisco right now.
The Chesapeake Bay Bridge Safety Enhancements Project in Maryland is about reinventing safety on one of the most critical and nerve-wracking crossings in the East Coast. Stretching 4.3 miles across the Chesapeake Bay, the Bay Bridge connects Annapolis on the western shore with Kent Island on the eastern shore. It carries over 25 million vehicles a year, but for decades, drivers dreaded it. Strong crosswinds, aging guardrails, and minimal emergency access made every crossing a gamble. By 2026, that's going to change. This proposed $280 million safety enhancement project focuses on storm hardening, real-time traffic management, and structural modernization, all while keeping the bridge operational. At the heart of the upgrade was the installation of wind protection barriers along the full span. These aerodynamic deflectors, engineered to reduce wind shear by up to 40%, now shield vehicles from dangerous gusts, especially those in high-profile trucks and SUVs. These barriers were manufactured in modular segments and lifted into place by high-lift barge-mounted cranes, operating only during low-traffic night windows. Equally transformative was the surface overhaul. Crews applied a high-friction epoxy overlay, a specialized treatment using resin mixed with aggregate, to improve tire grip during wet and icy conditions. This reduced crash rates by nearly 30% in early post-completion studies. To execute the work with minimal closures, workers used self-propelled modular transporters to bring in materials and machinery, keeping active traffic lanes free. Another major safety upgrade was the addition of intelligent lane control systems. Using overhead gantries, color-coded LED lane signals, and real-time sensors, the system can instantly change traffic direction during peak hours or emergencies. This system is tied to a centralized traffic command center in Annapolis, which also manages surveillance cameras, incident detection algorithms, and automated alerts for wrong-way drivers. Below the bridge, engineers conducted a full underwater retrofit. Divers working in pressurized suits and submersible remotely operated vehicles applied cathodic protection systems to the submerged piers. This electrochemical process prevents corrosion from salt water, extending the life of structure by decades. Meanwhile, seismic dampers were installed at key joints, providing additional stability during tremors or vessel strikes. The Bay Bridge now operates with a digital twin, a virtual, real-time model of the structure, updated through thousands of IoT sensors, tracking stress, vibration, temperature, and traffic loads. This data feeds into predictive maintenance models, allowing engineers to prevent failures before they happen. Rising from the ground in Orchard Park, New York, the new Highmark Stadium is a major construction endeavor aimed at delivering a state-of-the-art home for the Buffalo Bills and redefining the game day experience in Western New York. This open-air stadium replaces the aging original Highmark Stadium and is being built with a focus on durability, fan engagement, and advanced operational systems suitable for the harsh winter climate of the region. By 2026, the structural steel framing, precast concrete bowl, and building envelope are all projected to be complete, marking a major milestone in the stadium's delivery timeline. Construction began with extensive site grading and earthwork to shape the subgrade and install foundational infrastructure. The site preparation phase involved removal of unsuitable soils, installation of stormwater management systems, and placement of engineered fill to ensure proper compaction and drainage. Deep foundations using drilled shafts and large diameter piers were installed to support the stadium's superstructure, particularly beneath the main seating bowl and roof canopy supports. These foundations were embedded into the region's bedrock using high-capacity rebar cages and tremie-poured concrete to deliver structural stability under heavy snow and wind loads. Once the foundation work was finalized, erection of the stadium's structural steel frame commenced. Large steel columns and trusses were fabricated off-site and transported in segments to be assembled using high-capacity crawler cranes and bolted field connections. The steel structure forms the skeletal framework for the seating tiers, premium suites, press boxes, and canopy roof system. Parallel to this, precast concrete risers and seating platforms were installed in a stepped sequence to form the lower and upper bowls. These concrete components are cast with integrated utility conduits and anchorage points for seats, railings, and electrical fixtures. A major feature of the stadium is its asymmetrical canopy design, which is intended to shield the majority of fans from snowfall and wind while leaving the playing field open to the elements in true Buffalo fashion. The canopy is supported by a series of tapered box girders and cantilevered trusses extending outward from the upper bowl's compression ring. Roof decking includes insulated metal panels with integrated snow guards and drainage paths to direct meltwater safely to ground level. Mechanical, electrical, and plumbing systems have been progressing simultaneously with structural work. Central utility corridors were embedded into the lower levels, carrying chilled water, gas, electrical service, and communication cabling. Utility nodes are distributed throughout the concourses and suites to accommodate concession equipment, digital signage, lighting, and ventilation. High-efficiency HVAC units, snowmelt systems for walkways, and smart lighting controls are all part of the sustainable design strategy. By 2026, the entire stadium structure, including the concrete bowl and canopy roof, will be completed and fully enclosed. This enables interior fit-out phases to begin, which will involve installation of seats, finishes, digital infrastructure, and audio-visual systems. The building envelope, consisting of curtain wall glazing, insulated metal panels, and high-performance weatherproofing, will be sealed to withstand Western New York's freeze-thaw cycles and high wind events. Let's travel over to Carbon County, Wyoming, where the Chokecherry and Sierra Madre Wind Energy Project is set to become the largest onshore wind energy facility in the United States. The Chokecherry and Sierra Madre Wind Project is set to transform the energy landscape by providing up to 3,000 megawatts of electricity, enough to power nearly 1 million homes. By capitalizing on Class 6 and 7 wind resources of Wyoming, among the best in the nation, the project will significantly reduce carbon dioxide emissions by an estimated 7 to 11 million tons annually. Situated on approximately 320,000 acres of land south of Rawlins and Sinclair, this megaproject will comprise around 1,000 wind turbines installed in 2 phases. Phase 1 includes 225 turbines generating 1,500 megawatts, while Phase 2 adds approximately 375 turbines to reach the full 3,000 megawatt capacity. Despite the vast area, the actual surface disturbance is limited to less than 1,500 acres, preserving much of the natural landscape. To transmit the generated electricity to markets in the southwestern United States, the project integrates with the Transwest Express Transmission Project, a 732-mile high-voltage, direct current line connecting Wyoming to Nevada. This transmission line is crucial for delivering wind energy from Wyoming to high-demand areas like California, Arizona, and Nevada. With an estimated investment of $5 billion, this megaproject is a significant economic driver for Wyoming. During construction, it is expected to create over 1,000 temporary jobs and several permanent positions for operations and maintenance. Over its operational life, the project anticipates generating approximately $850 million in tax revenues, including property taxes, sales, use taxes, and wind electricity generation taxes. The construction of the Chokecherry and Sierra Madre Wind megaproject involves advanced engineering and logistics. Turbine components are transported via a new rail spur and distributed across the site using an extensive network of access roads. Given the strong and consistent winds of the area, construction activities are often scheduled during calmer periods to ensure safety and efficiency. The turbines, each with a capacity between 4 megawatt and 6 megawatt, are strategically placed to optimize energy capture while minimizing environmental impact. Currently, the construction is progressing steadily, with completion anticipated by 2026. The integration with the Transwest Express Transmission Project is also underway, ensuring that the generated wind energy will reach key markets in the southwestern United States. North of Dallas, in one of the fastest growing urban corridors in Texas, the Fields Entertainment District in Frisco is emerging as a large-scale, mixed-use mega-project that is actively under construction in 2026. The development is positioned within the broader Fields master-planned community, a multi-thousand-acre site designed to accommodate long-term population growth, corporate expansion, and regional tourism demand. The Fields Entertainment District is planned as a dense concentration of sports, hospitality, retail, dining, and public space, anchored by major destination users rather than traditional suburban commercial formats. Unlike single-purpose developments, the district is structured to operate continuously, supporting large events, daily foot traffic, and future transit-oriented growth. Its scale and phasing place it among the most consequential Dallas area mega projects progressing through construction in 2026. By 2026, horizontal infrastructure work is largely complete, allowing vertical construction to dominate activity across the district. Roadways, utility corridors, stormwater systems, and site grading were established in earlier phases, enabling simultaneous construction of multiple buildings. In 2026, cranes, concrete crews, and steel framing operations are active across entertainment venues, hotels, parking structures, and retail blocks. One of the primary construction focuses in 2026 is vertical development of large-format entertainment and event buildings. These structures require long-span steel framing, high-capacity foundations, and extensive back-of-house infrastructure. Construction includes structural steel erection, roof decking, and exterior enclosure systems designed to accommodate high occupant loads and advanced audiovisual systems. These buildings are engineered to support concerts, live events, and large public gatherings. Hospitality construction accelerates during 2026. Multiple hotel components within the district are rising simultaneously, with reinforced concrete and steel structures progressing floor by floor. Interior build-outs begin on lower levels as upper floors continue structural work. Mechanical and plumbing systems are sized for high turnover and large conference or event-driven occupancy patterns, reflecting the district's destination-oriented role. Retail and dining blocks are also under active construction in 2026. These buildings are designed with flexible floor plates to allow tenant customization while maintaining consistent architectural standards across the district. Construction includes storefront framing, exterior finishes, service corridors, and shared utility infrastructure. Emphasis is placed on pedestrian connectivity with covered walkways, plazas, and integrated outdoor seating areas built alongside vertical elements. Parking infrastructure represents a significant portion of 2026 construction activity. Multi-level parking garages are being built to serve entertainment venues, hotels, and retail uses. These structures require rapid cycle concrete construction and are designed with future adaptability in mind, allowing potential conversion or integration with autonomous or shared mobility systems later in the project's life cycle. Public realm construction expands significantly in 2026. Central gathering spaces, landscape plazas, and pedestrian spines are being formed as adjacent buildings reach enclosure stages. Hardscape installation, lighting systems, wayfinding infrastructure, and drainage features are constructed concurrently to ensure these spaces are operational as individual components of the district open. These areas are engineered to manage large crowd movements during peak events. Utility and systems integration is a major technical focus in 2026. Electrical substations, district-wide communications networks, and centralized security systems are being installed to support high-demand uses. Fiber networks are integrated throughout the district to support digital signage, ticketing systems, and event broadcasting. These systems are coordinated across multiple buildings to function as a unified operational environment. Well before the first match of the 2026 FIFA World Cup is played in North Texas, downtown Dallas is undergoing a coordinated series of infrastructure and venue upgrades that collectively form one of the region's most complex megaproject efforts active during 2026. Rather than a single construction site, the World Cup preparations consist of multiple overlapping projects focused on transportation, public space, security, mobility, and event operations, many of which reach peak construction or final delivery during 2026. The I-26 Widening and Connector Project in North Carolina is a milestone in Southern interstate modernization. Connecting Asheville to the South Carolina state line, I-26 has long served as a critical freight and commuter route, but over the years, this corridor became notorious for narrow lanes, dangerous curves, and bottleneck congestion, especially around the mountainous stretches near Asheville. The solution is a comprehensive $531 million mega project to widen, modernize, and realign the interstate for the demands of today and tomorrow. Completed in mid-2026, the project added 2 additional lanes in each direction, expanding the interstate from 4 to 8 lanes over more than 22 miles. This upgrade was a full redesign of critical infrastructure, including new interchanges, bridges, and a state-of-the-art connector that bypasses the tight downtown grid of the city. One of the most transformative components was the Asheville Connector, a newly built link that diverts long-haul traffic away from city streets. The construction involved extensive blasting, with crews using precision-controlled explosive charges to carve safe, stable roadbeds through the Blue Ridge Mountains. These cuts were reinforced with soil nail walls, rock anchors, and wire mesh sheeting, preventing landslides and erosion in the notoriously unstable terrain. The project also replaced and upgraded over a dozen bridges, including critical crossings over the French Broad River and multiple railroad tracks. Prefabricated steel girder assemblies were trucked in and lifted into place using hydraulic launching cranes during overnight closures. This minimized traffic disruptions and accelerated the construction timeline. In terms of smart infrastructure, the I-26 upgrade introduced real-time traffic monitoring systems, dynamic message boards, and road weather sensors embedded in the asphalt. These tools allow the North Carolina Department of Transportation to monitor traffic flow, redirect vehicles during incidents, and even issue automated warnings for fog, black ice, or severe rain. What truly sets this project apart is its strategic importance. I-26 is part of Corridor B of the Appalachian Development Highway System, linking inland manufacturing hubs to coastal ports in Charleston. With the new upgrades, the corridor can now accommodate larger freight volumes, faster emergency response, and safer civilian travel. With modern engineering, cutting-edge materials, and environmentally sensitive design, North Carolina has turned a regional liability into a national logistics asset, enhancing safety and economic mobility across the Southeast.
In 2026, one of San Francisco's most strategically important megaprojects under construction is taking shape across the Caltrain rail yards in the heart of central Soma. This isn't just a housing or transit upgrade. It's a massive reimagining of over 20 acres of publicly owned rail-adjacent land that has long divided the neighborhood. As construction pushes ahead this year, the rail yard redevelopment is steadily moving from planning to reality, with early phases under active build-out and long-term infrastructure elements aligning with the city's broader transit goals. Right now in 2026, the site is in the thick of foundational construction. Crews are laying the groundwork, literally, for what will eventually be a dense, mixed-use district layered above and around the working Caltrain tracks. This megaproject is part of a coordinated effort to modernize regional transportation while unlocking thousands of new homes and millions of square feet of development potential just blocks from downtown San Francisco. The Caltrain yard has been a physical and visual barrier in central Soma for generations. But in 2026, construction is actively transforming this space into an urban connector. Elevated platforms, decked structures, and street-level improvements are all in progress, designed to bridge the gap between surrounding neighborhoods and the core rail infrastructure. This year, much of the work focuses on realigning utilities, stabilizing the site for future vertical construction, and preparing parcels that will be used for new housing, office towers, and public spaces. The housing element of the rail yard redevelopment is one of the most anticipated components currently under construction. Phase 1 will deliver several hundred new residential units, with a significant portion allocated for affordable housing. These buildings, now rising on the edges of the yard, are expected to be ready for occupancy by 2028. Eventually, the full build-out will add thousands of homes to one of the city's most transit-rich locations, housing that is critically needed as San Francisco continues to face supply pressures. But housing is only one piece of this megaproject. In 2026, work is also underway on commercial development that will bring job space to the corridor, particularly targeting sectors like life sciences, tech, and creative industries. The close proximity to both downtown and future rail connections makes this site highly desirable, and the ongoing construction reflects the urgency to activate it. Several mid-rise office buildings are being framed out this year, with completion of the first wave of commercial space projected around 2029. A crucial component that's being integrated into the redevelopment in real time is transportation. The Caltrain facility itself is being reconfigured to prepare for electrification, high-speed rail integration, and potential undergrounding as part of the downtown rail extension. In 2026, While major tunneling has not yet reached the yard, planning and structural coordination are fully underway to make sure future rail service, including high-speed trains, can be accommodated. This makes the railyard site not just a place to live and work, but a critical node in the future of statewide transit.
The Grand Parkway expansion in Houston, Texas, is one of the largest highway infrastructure undertakings in the southern United States. Officially designated as State Highway 99, the Grand Parkway is a massive loop encircling the Houston metropolitan area. With rapid population growth and heavy commercial traffic burdening existing routes like I-10 and Beltway 8, this expansion was a logistical necessity. The segments H, I-1, and I-2, completed by late 2025, added over 52 miles of new highway lanes connecting Harris, Montgomery, Chambers, and Liberty counties. The final cost of the project exceeded $1.28 billion, financed through a combination of state funds and toll revenue bonds. The construction focused on 6-lane divided highways with full-grade separated interchanges, frontage roads, and intelligent traffic systems. Each segment was designed for heavy-load commercial vehicles, with pavement engineered to handle decades of truck traffic without structural degradation. What sets this project apart was the deployment of advanced construction technologies. Engineers used LiDAR-based terrain scanning and drone-assisted surveying to map flood-prone areas and adjust elevations accordingly. This was critical, given the vulnerability of Houston to flooding during hurricanes and storm surges. Geotextile reinforced soil embankments were employed to stabilize the ground, especially in the marshy zones of eastern Harris County. In terms of machinery, the expansion utilized automated paving machines, soil compaction drones, and mobile concrete batching units, which enabled high-speed, on-site mixing. To speed up bridge construction over waterways and railroads, teams deployed segmental bridge launching gantries. This allows entire spans to be placed without disrupting existing traffic or requiring extensive scaffolding. One of the biggest challenges was working around existing neighborhoods and ecosystems. The project included over 40 new wildlife crossings, sound barrier walls, and stormwater detention ponds to minimize environmental impact. The lanes were equipped with intelligent transportation system technology. Embedded sensors and cameras feed live data to control centers, enabling dynamic toll pricing, real-time traffic redirection, and emergency vehicle preemption systems. For commuters, the impact is already visible. A drive that once took 90 minutes during rush hour can now be completed in less than 45 minutes. Suburban areas like Cypress, New Caney, and Baytown are seeing a boom in residential development, thanks to improved access. For the trucking industry, the loop has shaved off millions in annual fuel and delay costs. The Grand Parkway expansion is a masterclass in how Texas handles growth, with speed, scale, and strategic vision. It moves economies, linking major ports, warehouses, and business parks into a single high-speed corridor. Downtown Dallas plays a central operational role in the World Cup, despite matches being hosted at AT&T Stadium in Arlington. The downtown core is designated as a primary fan destination, media hub, and hospitality center, requiring significant upgrades to handle international crowds, broadcast demands, and security requirements. As a result, construction in 2026 is distributed across transit corridors, public spaces, and city-owned facilities. Transportation upgrades are among the most visible construction activities in 2026. DART rail stations in and around downtown Dallas are undergoing platform improvements, accessibility upgrades, and system enhancements to accommodate higher passenger volumes. Construction includes platform resurfacing, expanded queuing areas, upgraded signage, and improved vertical circulation elements such as elevators and stairs. These projects are sequenced to maintain daily transit operations while accelerating work during off-peak periods. street-level infrastructure work intensifies in 2026. Key downtown corridors are being reconstructed or modified to improve pedestrian safety, crowd flow, and curbside operations. Construction includes widened sidewalks, improved crosswalk geometry, upgraded traffic signals, and reinforced pavement sections designed to handle buses, service vehicles, and temporary event traffic. Utility relocations accompany much of this work, requiring coordinated trenching and phased restoration. Public space upgrades represent another major component of 2026 construction. Downtown parks, plazas, and open gathering areas are being improved to serve as fan zones and event staging areas. Construction includes new hardscape surfaces, lighting systems, temporary infrastructure tie-ins, and expanded power and data capacity. These upgrades are designed to be permanent, allowing spaces to function year-round after the tournament concludes. Security-related construction advances significantly in 2026. Downtown facilities designated for World Cup operations receive perimeter hardening, controlled access points, and upgraded surveillance infrastructure. This includes installation of security bollards, reinforced barriers integrated into streetscape design, and expanded camera and monitoring networks. Much of this work is intentionally blended into public realm improvements to avoid long-term visual impact. Hospitality and event support infrastructure also sees targeted upgrades during 2026. Convention and meeting facilities in downtown Dallas undergo interior renovations to support media, operations, team logistics, and international broadcasting. Construction includes upgraded power distribution, enhanced telecommunications infrastructure, improved loading and service access, and reconfigured interior layouts to support temporary World Cup users. Wayfinding and signage infrastructure is another major focus in 2026. Crews install new directional systems designed for international visitors, incorporating multilingual signage and standardized event iconography. These systems are integrated into streets, transit stations, and public buildings, requiring coordinated installation across multiple agencies and property owners. Technology infrastructure work peaks in 2026 as well. Downtown Dallas receives expanded fiber optic capacity, upgraded wireless networks, and enhanced data redundancy to support global media transmission and high-density mobile usage. These installations often occur underground or within existing structures, making them less visible but critical to World Cup operations. From a construction sequencing perspective, 2026 is the final and most intensive year of preparation. Many projects that began in earlier years reach substantial completion during this period, while others undergo final fit-out, testing, and commissioning. The goal is to have all core infrastructure operational well before the tournament begins to allow for trial events, system testing, and security exercises. Temporary infrastructure planning also overlaps with permanent construction in 2026. Areas designated for fan festivals and live viewing require embedded connection points for temporary stages, screens, and crowd management systems. Construction teams install these features during permanent upgrades to avoid disruptive temporary installations later. The Helen Diller Medical Center at the University of California, San Francisco is one of the most advanced medical facilities ever built on the West Coast. Located at Parnassus Heights, this $4.3 billion megaproject, completed in 2026, stands as a fusion of cutting-edge healthcare, seismic engineering, and smart infrastructure. The University of California is a global leader in research and medicine, yet its aging hospital buildings were outdated and not up to the seismic safety mandates of California, with the state requiring all acute care hospitals to meet specific seismic regulations by 2030. UCSF acted early, building a structure that not only meets but exceeds the toughest standards for seismic resilience. At the heart of the facility is a 15-story medical tower with over 300 patient beds, 24 operating rooms, and expansive ICU and trauma units. It is designed to withstand a magnitude 8.0 earthquake, using base-isolated foundations and energy-dissipating steel bracing. This will allow the building to sway gently during seismic activity, minimizing damage and keeping operations running even in a disaster. The construction process was a feat of logistics. With limited space on the Parnassus Heights campus, contractors used vertical staging, off-site modular fabrication, and just-in-time material delivery to keep the site efficient. Tower cranes, robotic arms, and BIM software synchronized every phase, ensuring equipment installation, utility routing, and wall systems were aligned down to the inch. One of the standout features is the smart infrastructure of the facility. Every patient room includes real-time monitoring systems, adaptive lighting, and AI-powered diagnostic support terminals for clinicians. These systems communicate with the central data network of University of California, San Francisco, allowing remote specialists to consult in real time and reducing diagnostic errors by up to 30%. Sustainability was also a core pillar. The building meets LEED Platinum standards with solar panels, grey water recycling, triple glazed windows, and active chilled beam HVAC systems that cut energy consumption by 45% compared to traditional hospitals. The exterior features aluminum sunshades and vertical gardens that reduce solar gain and improve patient well-being. From a machinery standpoint, the project utilized automated concrete pumps, self-climbing formwork systems, and prefab MEP modules. The mechanical, electrical, and plumbing infrastructure of each floor was assembled off-site and hoisted into place like puzzle pieces, cutting installation time in half. Beyond the technology, what makes the Helen Diller Medical Center remarkable is its human-centered design. Large windows, rooftop gardens, calming interiors, and dedicated family spaces were all designed with input from patients, nurses, and doctors, a true reflection of community health priorities. Beneath the urban fabric of West Baltimore, one of the most significant rail infrastructure upgrades on the Northeast Corridor is unfolding with the Baltimore and Potomac Tunnel Replacement Project. This effort targets the elimination of a critical choke point where trains must slow to under 30 miles per hour to navigate through a pair of antiquated brick-lined tunnels built shortly after the Civil War. These tunnels, suffering from water infiltration, tight curvature, and poor vertical clearances, have long constrained passenger and freight operations. The new tunnel system, named the Frederick Douglass Tunnel, will consist of modern twin bores capable of supporting high-speed electric trains with full electrification, and by 2026, a substantial portion of the tunnel excavation and concrete lining work is expected to be completed. Initial stages of the project involved complex site preparation across multiple urban blocks. Utility relocation was one of the most challenging undertakings, as high-voltage electrical feeders, water mains, sewer lines, and communication ducts had to be rerouted or supported in place while maintaining service to surrounding neighborhoods. Surface access shafts were excavated using slurry wall techniques, allowing for deep vertical entry points that serve as launch and retrieval sites for tunnel boring machines. The TBMs used on this project are customized for soft ground tunneling with pressurized face systems to prevent ground settlement and surface disruption. As the TBMs advance, they simultaneously install precast concrete segment rings to form the tunnel lining. Each segment is bolted and gasketed to ensure watertight integrity. An annular grout is injected to fill the gap between the lining and the surrounding earth. To optimize logistics, a continuous muck removal system conveys excavated material through the tunnel to the surface, where it is processed and hauled away. Tunnel invert slabs and track bed preparation follow closely behind the TBM progress. This includes installation of reinforced concrete floors, embedded conduits for drainage and cabling, and future attachment points for the track slab. High-capacity ventilation ducts, lighting conduits, and emergency egress pathways are also integrated during this phase, allowing for a compact and efficient systems corridor. At ground level, the project includes new approach tracks and interlockings with modern signal systems. Work crews are laying new ballastless track using direct fixation methods, ideal for tunnels where precision alignment and vibration control are critical. Turnouts and crossovers near the portals are supported by precast plinths and coordinated with real-time signal interlock logic for safe switching operations. By 2026, the majority of tunnel excavation, structural lining, and invert construction will be finished, providing a continuous twin-tube shell beneath West Baltimore. Simultaneously, the construction of key ancillary facilities, such as traction power substations, ventilation shafts, and emergency exit buildings, will reach advanced stages of completion. These surface-level components are essential to the tunnel's overall operation and are built to withstand fire, seismic events, and external weather conditions.
On the eastern edge of San Francisco, where rusted cranes once loomed over a forgotten stretch of Shipyard, the Pier 70 redevelopment is one of the city's most ambitious megaprojects currently under construction in 2026. This historic industrial zone, nestled between the Dogpatch neighborhood and the bay, is being transformed into a vibrant waterfront community, one that blends housing, jobs, public parks, and restored heritage structures into a single cohesive district. The construction underway this year marks the most active phase of the project to date, with key milestones approaching as the site charges toward completion in the early 2030s. As of 2026, multiple parcels across Pier 70 are under simultaneous construction. Residential towers are climbing skyward, with the first phase of housing expected to be completed by 2027. These buildings will deliver nearly 1,100 homes in their initial stage, 25% of which are reserved as affordable housing. Construction crews are also working on major infrastructure upgrades across the site, including new streets, transit corridors, pedestrian paths, and shoreline protections to guard against sea level rise. The heart of the mega project is its connection to the past. Pier 70's redevelopment in 2026 doesn't erase its history, it builds on it. Several historic buildings are being restored and repurposed. These include old machine shops and steel foundries that once supported the shipbuilding industry. In 2026, many of these structures are undergoing seismic retrofitting and interior renovations to be converted into arts venues, retail hubs, and office space for design and tech firms. The goal is to preserve the gritty industrial character of the site while making it usable and vibrant for a 21st century city. Public space is a major focus of the construction effort in 2026. Over 9 acres of parks and waterfront access points are being built across the site. The highlight will be the large central green, an expansive park framed by restored industrial sheds and framed by views of the bay. As of this year, grading, drainage, and landscaping are underway, with full park openings projected for 2028. These open spaces are being built to double as climate infrastructure, designed to absorb stormwater, manage heat, and protect the site from flooding. In addition to housing and public amenities, the commercial component of Pier 70 is actively rising. Office buildings tailored to life sciences, technology, and creative industries are under construction now, with tenants expected to begin moving in by 2027-2028. These buildings are designed with flexibility in mind, featuring adaptive floor plans, outdoor terraces, and energy-efficient systems. Construction in 2026 is focused on delivering the first phase of these workspaces, helping to establish Pier 70 as an employment hub linked directly to the city's evolving economic base. The location is also a key asset. In 2026, construction crews are coordinating with transit agencies to enhance connections between Pier 70 and the rest of the city. Muni lines, bike lanes, and pedestrian links to the nearby Dogpatch neighborhood are all part of the ongoing infrastructure work. There's also future planning underway to accommodate ferry service, which would further connect the development to the regional transit network. When fully completed in the early 2030s, the Pier 70 redevelopment will deliver over 2,000 housing units, 2 million square feet of office and commercial space, 9 acres of parks, and over 300,000 square feet of retail, cultural, and community uses. But in 2026, it's the construction activity that defines the project. Foundation work, steel framing, historic preservation, and shoreline transformation all unfolding simultaneously.
Next up, we have to talk about the Portal North Bridge in New Jersey, a transformative infrastructure project set to redefine rail travel along the Northeast Corridor. The Portal North Bridge is a critical component of the broader Gateway program, aiming to enhance the reliability and capacity of the rail network between Newark, New Jersey, and New York City. The existing Portal Bridge, a 114-year-old swing-span structure over the Hackensack River, has long been a bottleneck, causing frequent delays due to its age and design limitations. The new bridge will replace this outdated infrastructure with a modern, fixed-span bridge, eliminating the need for openings to accommodate maritime traffic. This will significantly improve service reliability for both Amtrak and NJ Transit commuters. The project involves constructing a 2-track, fixed-span bridge rising 50 feet above the Hackensack River, allowing uninterrupted rail service while accommodating maritime navigation beneath. Spanning nearly 2.5 miles, the bridge will feature 3 massive tide arch spans, each weighing approximately 5 million pounds. These arches are being assembled off-site and transported via barge to the construction site for installation. The design eliminates movable components, reducing maintenance needs and enhancing operational efficiency. With a total project cost of approximately $2.3 billion, the Portal North Bridge represents a significant investment in the regional transportation infrastructure. Funding sources include federal grants, state contributions, and investments from Amtrak. The project is expected to generate substantial economic benefits, including job creation during the construction phase and improved connectivity that supports regional economic growth. The construction employs advanced engineering techniques and heavy machinery to handle the massive components involved. The tide arch spans are assembled at a fabrication facility and transported to the site using specialized barges. Heavy lift cranes and other equipment are utilized to position and secure these arches onto the bridge piers. The project also involves constructing deep foundations, retaining walls, and approach structures to integrate the new bridge seamlessly into the existing rail network. For now, the project has achieved significant milestones, with the final arch installed and overall construction approximately 80% complete. The bridge is on track for the first set of tracks to become operational in the second half of 2026, with full project completion anticipated by 2027. These developments mark a significant step forward in modernizing the Northeast Corridor and enhancing the reliability of rail service for hundreds of thousands of daily commuters. Far south of Dallas, in Ellis County, near the city of Midlothian, the Google Data Center campus stands as one of the most infrastructure-intensive megaprojects under construction in the North Texas region in 2026. Unlike high-visibility urban developments, this project is defined by scale, power demand, and systems complexity, with construction activity focused on creating long-term digital infrastructure rather than public-facing architecture. The Midlothian data center is part of Google's broader expansion of hyperscale computing capacity in Texas, selected for its access to land, transmission infrastructure, and regional redundancy. The site is planned as a multi-building campus rather than a single structure, allowing phased expansion over several years. This phased approach makes 2026 a key construction year, as initial facilities transition from shell construction to systems-heavy build-out. By 2026, site-wide civil and utility infrastructure is largely established, enabling vertical construction and interior fit-out to dominate activity. Primary data hall buildings are either topped out or approaching structural completion, with reinforced concrete frames and steel roof systems designed to support heavy mechanical loads. These structures prioritize clear spans, high floor loading capacity, and modular expansion potential. Mechanical and electrical construction is the defining feature of 2026 work. Crews are installing large-scale power distribution systems, including substations, switchgear yards, and redundant electrical pathways. Multiple layers of redundancy are built into the campus, requiring parallel systems for primary and backup power. This includes integration with regional transmission lines and on-site backup generation infrastructure. Cooling infrastructure is another major focus during 2026. Data center cooling plants, including cooling towers, chillers, and water treatment systems, are under active construction. These systems are designed to handle continuous high-density server loads while optimizing water and energy efficiency. Piping networks connecting cooling plants to individual data halls are installed underground and within service corridors throughout the campus. Interior build-out of data halls accelerates in 2026. Raised floor systems or slab-integrated airflow designs are installed depending on building configuration. Server rack infrastructure, cable trays, and fire suppression systems are constructed in tightly sequenced phases. Fire protection systems typically use specialized suppression methods designed for sensitive electronic environments, requiring extensive testing and commissioning. Support buildings and ancillary facilities are also under construction in 2026. These include network operations centers, security facilities, maintenance buildings, and office space for on-site technical staff. These structures are less visually dominant, but critical for day-to-day operation and monitoring of the data center campus. Security and perimeter infrastructure advances significantly during 2026. The site includes layered physical security systems such as perimeter fencing, controlled access points, surveillance infrastructure, and secure internal zoning. Much of this construction is integrated into site grading and landscaping to maintain operational separation without excessive visual impact. Water and environmental infrastructure remains active throughout 2026. New water supply connections, storage tanks, and wastewater systems are completed or expanded to support cooling operations. Stormwater management features, including retention ponds and drainage systems, are finalized to meet regulatory requirements and protect surrounding land from runoff impacts. From a timeline perspective, 2026 represents a transition from heavy shell construction to commissioning-focused activity. While new buildings may still be under construction, several completed structures enter systems testing phases. Electrical load testing, cooling system commissioning, and network validation are conducted incrementally as each facility segment reaches readiness. Construction activity is expected to continue beyond 2026, with additional data halls and support facilities added in subsequent phases. Full campus build-out is typically planned over multiple years, allowing capacity to scale with demand. Initial operational capability is often achieved before total completion, with sections of the campus coming online independently. Let's move over to the Empire Wind, one project, a transformative offshore wind initiative poised to reshape the energy landscape of New York. Empire Wind 1 is a cornerstone in the ambitious plan of New York to achieve 9,000 megawatts of offshore wind energy by 2035. With a capacity of 810 megawatts, this project is designed to supply clean electricity to approximately 500,000 homes in New York City, significantly reducing greenhouse gas emissions and advancing the climate goals of the state. Located about 15 to 30 miles southeast of Long Island, Empire Wind 1 encompasses an area of 80,000 acres. The project will consist of 54 Vestas, 15 megawatt wind turbines, each standing over 850 feet tall, making them some of the largest and most powerful turbines in operation. These turbines will be connected via subsea cables to an onshore substation at the South Brooklyn Marine Terminal in Sunset Park, Brooklyn. From there, electricity will be transmitted to the Gowanus substation, integrating seamlessly into the power grid of New York City. The estimated investment for Empire Wind 1 is around $2.5 billion. Beyond providing renewable energy, the project is expected to generate significant economic benefits, including the creation of over 1,000 union jobs during the construction phase and approximately 300 long-term jobs for operations and maintenance. The redevelopment of South Brooklyn Marine Terminal into a state-of-the-art offshore wind port facility is also anticipated to stimulate local economic activity and establish a robust supply chain for future offshore wind projects. The construction of Empire Wind 1 involves advanced engineering and specialized equipment, including heavy lift vessels used for transporting and installing massive turbine components at sea. Jack-up rigs provide stable platforms for turbine installation in deep waters. Horizontal directional drilling employed for laying subsea cables with minimal environmental impact, while aircraft detection lighting systems are integrated into turbines to minimize light pollution by activating lights only when aircraft are detected. Currently, the Empire Wind 1 has achieved several critical milestones. The Bureau of Ocean Energy Management approved the construction and operations plan in February 2024, allowing construction to proceed. However, in April 2025, the U.S. Department of the Interior issued a halt to construction, citing the need for further environmental review. In the midst of a sweeping modernization effort to upgrade the vital Northeast Corridor rail line, the Portal North Bridge Replacement Project in New Jersey stands out as a transformative undertaking that directly addresses one of the most notorious infrastructure bottlenecks in the region. Originally constructed in 1910, the existing Portal Bridge was a swing-span design that rotated horizontally to allow marine traffic to pass on the Hackensack River. This outdated mechanism frequently jammed, misaligned, or failed to lock properly, resulting in delays cascading throughout Amtrak and NJ Transit Rail operations. The new Portal North Bridge, scheduled to reach substantial completion by 2026, is being constructed to completely eliminate these issues by replacing the antiquated swing bridge with a high-level, fixed-span structure that no longer needs to open for river traffic. Construction of the new bridge began with extensive site preparation, including the relocation of utility lines, clearing of right-of-way areas, and installation of cofferdams in the river to allow work in dry conditions. The foundation phase focused heavily on deep foundation elements to support the massive structure. Driven steel piles and drilled shafts were installed to reach down through layers of river sediment and into bedrock, ensuring the bridge could carry modern rail traffic loads while withstanding hydraulic and seismic stresses. Each pier footing was constructed within these cofferdams using reinforced concrete forms designed to resist buoyant forces from the surrounding water. One of the central design improvements is the elevation of the new fixed bridge approximately 50 feet above mean high water, which accommodates all standard maritime traffic underneath without requiring movable components. The bridge spans approximately 2 miles in total length, incorporating approach viaducts and embankments that gradually rise to meet the central structure. To construct these approach sections, engineers deployed precast concrete girders supported on reinforced piers, enabling repetitive modular assembly with minimized disruption to existing rail operations. The steel superstructure of the main span was fabricated off-site and delivered in large segments. Each segment was hoisted into place using heavy lift cranes operating from barges and temporary trestles erected in the river. The steel girders were bolted and welded together atop temporary falsework, after which the concrete deck was poured using a stay-in-place formwork system. This method ensured tight construction tolerances and allowed simultaneous work on electrical systems and track installation above. Signal and catenary system integration was a major component running in parallel with structural work. Crews installed new overhead contact system poles and strung high-tension wire throughout the new bridge alignment. Track-laying teams followed closely behind, securing continuous welded rail onto concrete ties using high-precision tamping and alignment equipment. Positive train control systems were incorporated into the new signal infrastructure, bringing the bridge in line with modern safety and automation standards.
Buried beneath the surface of San Francisco's downtown in 2026 is one of the city's most consequential megaprojects under construction, the Portal, also known as the Downtown Rail Extension. This massive underground infrastructure project is finally being realized after decades of delays, aiming to connect Caltrain and eventually California's high-speed rail directly to the Salesforce Transit Center. As of this year, excavation work is ramping up, tunneling contracts are active, and the city is fully committed to completing the extension by the early 2030s. In 2026, the Portal is a hive of subterranean activity. Tunnel boring preparations are in progress, utility relocation is underway, and major downtown streets are experiencing stage disruptions as crews create access points for the underground guideways. It's one of the most complex transportation builds in the Bay Area, requiring coordination beneath some of the densest blocks in the city. Once complete, this megaproject will deliver a seamless rail connection from the peninsula and Central Valley straight into the financial core of San Francisco. The project involves building approximately 1.3 miles of new track, mostly underground, to link the existing Caltrain line near 4th and King with the Salesforce Transit Center. In 2026, the staging areas at both ends of the project are fully operational. Pile driving, shoring walls, and structural reinforcements are all happening in real time as the city begins to carve out the physical corridor that will carry thousands of passengers daily. Construction in and around Townsend, 2nd Street, and the south of Market area is active and accelerating, with visible impacts above ground and substantial progress being made below it. The Portal isn't just a rail project, it's a regional unlock. In 2026, Caltrain still terminates at 4th and King, about a mile short of downtown. That last mile has long been the missing link in Bay Area transit. By closing that gap, this project will plug regional rail directly into San Francisco's business core, reducing car dependency and reshaping how people move across the region. When complete, the Portal will allow Caltrain riders to disembark in the heart of the city and will set the stage for future high-speed rail service to run directly from Los Angeles to downtown San Francisco, without transfers. The current timeline targets a completion date in the early 2030s, with most heavy construction expected to occur between 2026 and 2030. In the context of San Francisco's other megaprojects under construction right now, the portal stands out for its invisibility. Most of the work is happening underground, but the scale of its impact will rival that of any tower or waterfront redevelopment. Cost is high, risk is real, and coordination is intense. Crews are navigating under live utilities, major foundations, and transit lines. Every foot of tunnel requires precision, and every stage of construction must account for seismic resilience, waterproofing, and integration with existing BART and MUNI infrastructure. In 2026, engineering teams are deep into geotechnical work and soil stabilization, preparing for the eventual tunnel boring operations that will begin in earnest in 2027.
Amid the complex subterranean infrastructure of New York City, the 2nd Avenue Subway Phase 2 project represents a major expansion of transit capacity along Manhattan's East Side, particularly servicing the underserved East Harlem neighborhood. This phase extends the Q line northward from the current terminus at 96th Street up to 125th Street, adding approximately 1.5 miles of new twin-track tunnel and 3 new stations at 106th Street, 116th Street, and 125th Street. Although full completion is expected later, significant early works, tunneling activities, and utility relocations are on schedule to be finalized by 2026, marking a critical milestone in the overall construction timeline. Initial construction efforts have focused on the relocation and protection of underground utilities, a process that requires precision excavation through layers of densely packed infrastructure, including sewer lines, water mains, gas conduits, electrical cables, and telecommunication systems. To accomplish this safely, crews utilized vacuum excavation methods and non-destructive digging tools, mapping utility alignments and rerouting them to clear paths for future excavation. In some areas, new utility corridors were built entirely to support the tunnel boring operations and future station development. Once the utility work reached sufficient progress, tunneling operations commenced with the deployment of tunnel boring machines that were lowered into deep launch boxes constructed along the alignment. These TBMs are massive cylindrical machines equipped with rotating cutter heads designed to bore through Manhattan schist and other geologic layers. As they advanced, the machines simultaneously installed precast concrete tunnel lining segments, forming the structural shell of the subway tunnels. The twin tubes are built with precise curvature and grade to meet performance standards for modern train speeds and passenger comfort. In parallel with tunneling, deep excavation began for the future station caverns. Each station box, particularly the 125th Street terminal, is being constructed using a combination of cut and cover methods and sequential excavation techniques where appropriate. For deeper sections, rock blasting and mechanical excavation were employed under controlled conditions, with vibration monitoring in place to protect surrounding buildings and infrastructure. Excavated material is removed using muck conveyors and trucked out via dedicated access shafts. One of the most significant aspects scheduled for substantial completion by 2026 is the structural excavation and primary concrete shell of the 125th Street station. This includes the reinforced concrete station box, invert slab, and column and beam framework that will support platform levels, mezzanines, and ancillary rooms. The work also encompasses critical elements of vertical circulation infrastructure such as elevator and escalator shafts. Completion of this shell by 2026 will allow fit-out phases such as mechanical, electrical, and plumbing installation to begin immediately thereafter. Throughout the alignment, permanent structural support systems like slurry walls, rock bolts, shotcrete linings, and waterproofing membranes are being installed in stages, often following close behind excavation fronts. Utility infrastructure is being rebuilt to modern standards with upgraded capacity, redundant power feeds, and new stormwater management systems. By 2026, the completion of tunneling, station cavern excavation, and core structural concrete work marks a pivotal transition point in Phase 2 of the 2nd Avenue subway. It sets the stage for the interior outfitting, systems installation, and track work that will follow, ultimately advancing the long-awaited goal of extending high-capacity subway access to communities that have endured generations without it.
The G Line, formerly known as the Orange Line, was never designed to stay the same. From the beginning, it was a workaround, a bus rapid transit route built in place of a rail line due to funding constraints and political compromise. But over time, its ridership and strategic location forced the city to rethink what it could be. Now the G Line is undergoing a major transformation, an infrastructure upgrade project spanning the entire 18-mile corridor through the San Fernando Valley, pushing the limits of what bus transit can do in Los Angeles. The goal is simple: increase speed, capacity, and safety. But executing that goal has required deep and complex engineering interventions at nearly every point along the route. One of the most critical changes is the installation of a state-of-the-art signal priority and preemption system. Unlike traditional traffic signals that respond to fixed timers or limited sensors, this system actively clears intersections ahead of approaching buses, reducing delays and allowing for smoother flow across dozens of street crossings. Another major element is the construction of grade separations, rail-style overpasses and underpasses at the busiest and most delay-prone intersections. Key locations like Sepulveda Boulevard, Van Nuys, and others are being excavated and rebuilt with concrete bridges and undercrossings to allow buses to pass through without ever stopping for cross-traffic. These structures require complex retaining wall systems, traffic rerouting, and in some cases, full reconstruction of local street infrastructure around the new grades. To support higher frequency service, the corridor is being outfitted with new power systems, bus-only lanes resurfaced with heavy-duty concrete, capable of supporting constant vehicle weight, and upgraded station platforms. The existing asphalt guideway, originally built to mimic light rail tracks in layout, has been deteriorating under the strain of articulated buses. Rebuilding it requires full-depth removal and replacement with reinforced concrete slabs, tied into a subsurface drainage system to prevent water intrusion and pavement shifting over time. Platform upgrades go beyond aesthetics. Stations are being lengthened to accommodate longer, higher-capacity buses and future electric models. Each platform is being raised and re-leveled to allow for near-zero gap boarding, speeding up passenger flow and improving accessibility. Integrated electrical conduits and utility vaults are also being installed during construction to prepare for future overhead charging systems as the fleet transitions to full electric. A core part of the upgrade involves upgrading the actual vehicle fleet. Metro is phasing in battery electric buses with larger passenger capacities, regenerative braking systems, and onboard diagnostics. These buses weigh more than their natural gas predecessors, which has direct implications for bridge loading, braking distances, and pavement wear. Engineers had to revisit structural tolerances across the entire corridor, from culverts and embankments to turning radii and clearance zones, to ensure long-term durability under heavier rolling stock. Fiber optic lines are also being laid alongside the corridor to support real-time monitoring. Everything from vehicle location, signal interaction, passenger load, and environmental data will be fed into Metro's central control center. This data will be used not just for dispatch, but to dynamically adjust signal cycles and reroute in case of emergencies. Drainage systems along the G Line were never built for current-day storms. As part of the upgrade, culverts are being expanded, bioswales are being added to medians, and runoff channels are being lined with concrete and fitted with sensors to monitor flow levels during heavy rain. All of this is necessary to prevent trackway flooding and preserve the subgrade from erosion.
Long before Miami's skyline signaled its rise as a global city, the expansion of Port Miami and its tunnel interchanges quietly re-engineered the region's economic foundation through one of the most consequential infrastructure megaprojects in the county's history. Port Miami, located on Dodge Island in Biscayne Bay, underwent a coordinated expansion program during the late 2000s and early 2010s, aimed at transforming the port into a post-Panamax global trade hub. This effort combined portside construction, navigational improvements, and highway-grade tunnel interchanges into a single integrated mega-project. The goal was to remove physical, maritime, and logistical constraints that limited cargo growth while separating freight movement from downtown Miami's surface streets. One of the earliest and most critical construction components was the deepening of the port's main navigation channel. Prior to expansion, the channel depth restricted access for larger container vessels. Dredging operations began in the early 2010s and involved removing millions of cubic yards of material from Biscayne Bay to achieve a depth of approximately 50 to 52 feet. This work was completed in 2015, timed to coincide with the expanded Panama Canal, allowing Port Miami to receive fully loaded post-Panamax container ships for the first time. On Dodge Island itself, extensive terminal reconstruction took place in parallel with dredging. Older cargo berths were demolished and rebuilt with reinforced concrete wharves capable of supporting heavier cranes and higher container loads. New gantry cranes, some of the largest in the world at the time of installation, were erected on reinforced rail systems embedded into the key structure. Yard areas were regraded and paved to accommodate automated container handling equipment and higher stacking densities. Utility infrastructure beneath the port was also rebuilt. This included new electrical substations, stormwater drainage systems, fuel distribution lines, and communications networks designed to support modern terminal operations. These upgrades were completed incrementally to avoid disrupting ongoing cargo and cruise activity, requiring phased construction zones across the island. The landside component of the expansion centered on the Port of Miami Tunnel and its highway interchanges, which together form the port's primary freight access system. Construction of the tunnel began in 2010 and was coordinated directly with port expansion schedules. The tunnel consists of two submerged roadway tubes connecting Dodge Island to Watson Island, bypassing downtown Miami entirely. Equally significant were the tunnel interchanges themselves. On the mainland side, major roadway reconstruction was required to tie the tunnel directly into Interstate 395 and Interstate 95. This involved building new elevated ramps, retaining walls, and transition structures capable of handling heavy truck volumes at highway speeds. Existing roadways were demolished and realigned, with traffic maintained throughout construction using temporary detours and phased lane shifts. On the port side, Dodge Island underwent extensive reconfiguration to integrate tunnel portals with internal port circulation. New access roads were built, grade separations installed, and security checkpoints relocated to streamline truck movement. These changes allowed cargo vehicles to enter and exit the port without crossing cruise passenger traffic, significantly improving operational efficiency and safety. The tunnel excavation itself was completed in 2013, but the interchange construction and systems integration extended into 2014. The full tunnel and interchange system opened to traffic in August 2014, marking a major milestone in the port expansion timeline. From that point forward, thousands of trucks per day were rerouted away from downtown Miami streets and directly onto the interstate network. The expansion program also included rail infrastructure improvements. Port Miami's on-dock rail connection was rehabilitated and reactivated, linking the port directly to Florida East Coast railway lines. Track upgrades, switching yards, and loading areas were constructed to enable intermodal freight transfer, reducing dependence on trucking for long-haul cargo movement. In the context of Miami's biggest megaprojects, the Port Miami expansion and tunnel interchanges differ from high-rise developments by operating as a systems-level transformation. The project did not create a single landmark structure, but instead rebuilt the physical processes that allow the city to function as a logistics hub. Its completion aligned with other regional megaprojects, including airport cargo expansion and downtown redevelopment, forming an interconnected infrastructure network.
Tucked just south of downtown Los Angeles, Exposition Park has always been a place of ambition, home to world-class museums, the LA Memorial Coliseum, and the beating heart of the city's cultural and sporting life. But what's unfolding there now isn't just an upgrade. It's a full-scale transformation, timed to align with the arrival of the 2028 Olympic Games. This is the Exposition Park expansion, and it's one of the most concentrated, multi-layered megaprojects happening anywhere in the city. We're talking about more than 100 acres of dense, high-profile development. The kind of space where architecture, infrastructure, landscape, and engineering have to work in seamless coordination. And every inch of it is being reimagined, stitched together into a new kind of urban park. One that blends Olympic-scale sports facilities with civic space, transit access, and cultural presence. At the center of this expansion is the Lucas Museum of Narrative Art, an enormous, fluid, almost spaceship-like structure that defies traditional design logic. Spanning over 300,000 square feet, the building floats above the landscape on concrete pylons, allowing for an uninterrupted park to run beneath it. Engineering that vision into reality meant solving a long list of structural challenges. The museum's form curves and bends with few right angles, requiring a steel skeleton unlike any conventional grid. Every beam had to be custom fabricated. Load paths had to be recalculated from scratch. But that's only one piece. Adjacent to it, new Olympic training facilities are being added in and around the Coliseum, including athlete, housing, high-performance sports labs, and temporary structures built to IOC standards. These aren't off-the-shelf projects. Each facility must meet international competition criteria while being adaptable for post-games public use. That means flexible infrastructure, modular designs that can expand or collapse depending on future needs, and utility corridors capable of serving both a global broadcast event and a local youth sports league. A new mobility hub is also under construction, tightly integrated with the K Line, Crenshaw LAX Line, regional bus service, and pedestrian corridors linking USC, the Natural History Museum, and BMO Stadium. This isn't just about moving people, it's about rethinking access. Engineers are embedding smart traffic systems, ADA upgrades, secure bike lanes, and crowd flow modeling to handle Olympic-scale surges without overwhelming local streets. Then there's the landscape itself. More than 14 acres of new green space are being carved into the existing grid, with bioswales, permeable pavement, and stormwater recycling systems hidden beneath sculpted terrain. Everything is dual purpose. That shaded plaza? It's also an emergency egress route. That rolling hill. It's backfilled over a utilities corridor with seismic isolation joints. Every tree and trail was designed not just for beauty, but for function, cooling microclimates, guiding crowds, and managing runoff during rare but intense LA storms. Beneath the surface, the engineering complexity continues. Utility upgrades, electric, water, fiber, gas, are being laid out like a circulatory system for a future-proof urban core. Crews had to dig and trench with surgical accuracy, often working just inches away from existing structures that couldn't be moved or shut down. Phasing the construction without interrupting events at the Coliseum or the Museum District meant round-the-clock scheduling, heavy prefabrication, and just-in-time delivery logistics.
Beneath Biscayne Bay, hidden from the skyline that defines Miami's megaproject boom, the Port of Miami Tunnel represents one of the most complex and consequential infrastructure projects ever built in South Florida. The Port of Miami Tunnel was designed to directly connect Dodge Island, home to Port Miami, with the interstate highway system, creating a dedicated underground freight corridor between the port and Interstate 395 and Interstate 95. Before the tunnel, cargo trucks were forced to move through downtown Miami streets, creating chronic congestion, safety issues, and delays that constrained the port's growth. The tunnel fundamentally restructured how goods move through the city, making it a critical component of Miami's broader mega-project transformation. Planning for the tunnel began decades before construction, with serious development efforts accelerating in the early 2000s as Port Miami expanded into a major global cargo and cruise hub. Construction officially began in 2010, after years of environmental review, financing negotiations, and engineering studies. The project was delivered through a public-private partnership, an uncommon approach at the time for U.S. transportation megaprojects, involving the Florida Department of Transportation and a private concessionaire responsible for design, construction, financing, and long-term operation. The construction scope centered on two parallel tunnel tubes, each approximately 3,900 feet long, bored beneath Biscayne Bay. The tunnels were excavated using a massive tunnel boring machine specifically designed to operate in Miami's challenging geology, which consists of porous limestone, sand, and a high water table. The tunnel boring machine, weighing thousands of tons, was launched from Watson Island and advanced underwater toward Dodge Island, cutting through bedrock while simultaneously installing precast concrete liner segments to stabilize the tunnel walls. Excavation operations required continuous groundwater management and precise pressure control to prevent collapse or water intrusion. The tunnel alignment passed beneath active shipping channels, requiring careful coordination to avoid disrupting port operations and marine traffic. Spoil material removed during tunneling was transported and processed without interfering with surrounding urban and maritime infrastructure. In addition to the underwater tunnels, the project included extensive cut and cover construction on both ends. On Watson Island and Dodge Island, large access portals were excavated, requiring dewatering systems, retaining walls, and deep foundations to support the tunnel entrances. New roadway interchanges were built to connect the tunnel directly to I-395, eliminating truck traffic through surface streets in downtown Miami. Construction also included advanced ventilation buildings, fire suppression systems, emergency cross passages between tunnel tubes, and real-time monitoring systems. These safety features were essential to meet federal highway tunnel standards and ensure continuous operation in a hurricane-prone region. The tunnel was engineered to withstand storm surge, seismic forces, and long-term exposure to saltwater conditions. The project faced multiple technical and schedule challenges during construction. Delays occurred due to mechanical issues with the tunnel boring machine, groundwater infiltration events, and the complexity of working beneath an active port and bay. Despite these challenges, tunneling was completed in 2013, marking one of the most technically demanding phases of the project. Following structural completion, several years were dedicated to roadway finishing, systems installation, testing and commissioning, ventilation, lighting, traffic control, and emergency systems underwent extensive testing before the tunnel was open to traffic. The Port of Miami Tunnel officially opened in August 2014, completing a construction timeline of roughly 4 years. Within the context of Miami's biggest mega projects, the Port of Miami Tunnel stands apart from high-rise developments like Panorama Tower or Brickell City Centre. Rather than reshaping the skyline, it reshaped the city's logistical foundation. By removing thousands of trucks per day from downtown streets, the tunnel enabled parallel megaprojects in residential, commercial, and cultural development to proceed without freight congestion, limiting growth.
Where the Port of Los Angeles meets the open Pacific, a vast transformation is underway. Once a place defined by rusted cranes and abandoned warehouses, San Pedro's historic waterfront is being reimagined as a massive public destination. This is West Harbor, a $500 million redevelopment project that's reshaping 42 acres of prime harborfront land into one of the largest and most ambitious waterfront revitalizations in California history. For decades, the San Pedro waterfront was a place of industry. Cargo ships, rail lines, and container yards dominated the landscape, cutting the community off from its own shoreline. The ocean was always there, visible but unreachable. The idea behind West Harbor was radical in its simplicity. Take land that had long been the realm of cranes and commerce and return it to the people. Replace the shipping yards with open promenades. Tear down the fences, open the gates. But turning a gritty, industrial port into a modern, urban waterfront park isn't just a matter of cosmetics. It's an enormous engineering challenge. Beneath the surface, the ground itself needed rebuilding. Years of marine traffic, heavy equipment, and salt exposure had weakened bulkheads and corroded old pilings. Before a single restaurant could open, crews had to stabilize the soil, drive hundreds of deep foundation supports, and upgrade the harbor's edge to withstand both tidal surges and seismic shocks. At the heart of the project is a massive promenade that wraps along the water, designed not just for pedestrians, but for resilience. The concrete pathways are elevated to anticipate sea level rise, with drainage systems engineered to handle storm surges from both land and ocean. New docks are being constructed to support visiting ships and harbor cruises, each one designed with floating gangways that rise and fall with the tides, maintaining access even in extreme conditions. West Harbor isn't just infrastructure, it's experience. The development includes over 150,000 square feet of space for retail, dining, and entertainment, with anchor tenants ranging from artisan markets to major restaurants. A 6,200-seat outdoor amphitheater is being built directly on the waterfront, engineered to deliver concert-quality acoustics in a coastal environment, where sound bounces unpredictably off water and wind. Engineers had to design the stage foundation to accommodate both musical events and the occasional pounding from Pacific storms, using vibration damping, materials, and reinforced steel substructures. All of this, performance spaces, restaurants, shops, sits on land reclaimed from decades of industrial use. That meant a full environmental remediation process, involving soil testing, removal of contaminated fill, and installation of modern stormwater systems to prevent runoff from polluting the bay. A particularly complex element was integrating the new West Harbor seamlessly with the surrounding transportation network. This meant widening roads, building new intersections, and coordinating with nearby freight operations, all while preserving the historic landmarks that give San Pedro its identity. The historic battleship Iowa, docked nearby, had to be factored into every phase of design, ensuring visitor access remained open during construction. The engineering teams also had to work in parallel with the Port of LA's ongoing operations, scheduling pile driving and crane activity to avoid disrupting maritime logistics. Even as the heavy machinery rolls and concrete is poured, the bigger vision is already taking shape. This isn't just about leisure. It's about reconnecting a city with its coastline. For generations, San Pedro's waterfront was a wall of industry. West Harbor turns it into a front porch.
Covering more than 27 acres across multiple downtown blocks, Miami World Center is not a single construction project, but a layered mega project built through coordinated phases that collectively reshaped the northern edge of downtown Miami. Miami World Center is located north of the Central Business District, bounded generally by Northeast 2nd Avenue, Interstate 395, and Northeast 8th Street. The site consisted for decades of underutilized parcels, surface parking, and fragmented low-rise structures. Formal planning for redevelopment began in the early 2000s, with land assembly occurring gradually over many years. The scale of the site required a master-planned approach rather than a single build execution. Major construction activity began in the mid-2010s, following zoning approvals and infrastructure agreements with the City of Miami and Miami-Dade County. Early phases focused on horizontal construction, including demolition, mass grading, utility relocation, and the installation of new underground infrastructure. Water, sewer, power, communications, and stormwater systems were rebuilt to support millions of square feet of future development. A defining construction element of Miami World Center was its internal street grid. New public streets were carved through the site, requiring roadway construction, drainage systems, sidewalks, lighting, and streetscape elements. These streets were designed to function as permanent city infrastructure rather than private access roads, integrating the development into the surrounding urban fabric. Vertical construction followed in multiple, overlapping phases. Residential towers were among the first major structures to rise, each requiring deep foundations suited to Miami's limestone geology and high groundwater conditions. Pile foundations, reinforced concrete cores, and high-rise flat-plate floor systems were used across most towers, with construction sequenced to allow simultaneous builds on adjacent parcels. Retail and commercial structures were developed at the podium and street levels. These buildings required large-span structural systems to create flexible interior layouts for tenants. Mechanical and electrical systems were distributed through shared service corridors to reduce redundancy across the district. Loading docks and service access points were consolidated to minimize street-level disruption. One of the most significant infrastructure integrations within Miami World Center was its relationship with regional transit. The development was designed around proximity to Brightline's Miami Central Station, as well as Metro Rail, Metro Mover, and bus connections. Pedestrian corridors and public spaces were constructed to funnel foot traffic between transit nodes and interior blocks, requiring careful grading and structural decking over below-grade utilities. Construction timelines varied by parcel. Early residential and retail components began delivering units around 2018 and 2019. Additional towers and commercial buildings were completed in the early 2020s, with construction continuing in phases as market conditions and financing allowed. Unlike a single mega project with a fixed end date, Miami World Center evolved through staggered completions. Hotel construction formed another major component. Large hospitality structures required distinct structural and mechanical systems, including back-of-house service cores, conference, spaces, and rooftop amenities. These buildings were constructed concurrently with residential towers, increasing logistical complexity across the site. Parking infrastructure was largely integrated into podiums and below-grade levels. This required excavation, dewatering, and reinforced slab construction beneath active building sites. Parking systems were designed to serve multiple uses, including residential, retail, and event traffic, reducing the need for standalone garages. From a construction management perspective, Miami World Center required coordination across dozens of contractors, architects, and engineers. Crane operations, concrete pours, and material deliveries were scheduled to avoid conflicts within a dense, active site. Safety planning was critical due to the proximity of Interstate 395 and ongoing city traffic. The megaproject also included public space construction, such as plazas and pedestrian promenades. These areas required structural support for landscaping, irrigation systems, and integrated lighting. Public realm construction often occurred late in each phase, following heavy structural work.
Jordan Downs wasn't built to last, but it lasted. What began in the 1940s as temporary war worker housing in the heart of Watts evolved into one of Los Angeles's most recognized public housing projects. For decades, it stood as a symbol of neglect, of disinvestment, of the city's fractured promises. Now it's at the center of one of the largest and most complex urban redevelopments ever attempted in Southern California. This is the Jordan Downs redevelopment, a multi-phase billion-dollar megaproject that's rebuilding an entire neighborhood from the ground up. We're not talking about a simple renovation. This is full-scale urban reconstruction, replacing over 700 aging public housing units with a mixed-income community of more than 1,400 new homes, complete with parks, retail corridors, a new street grid, and state-of-the-art infrastructure. And all of it is happening while people still live there. That reality, redeveloping a live-in community without displacement, is what makes this project such a massive logistical and engineering challenge. Everything had to be phased. Crews couldn't just level the site and start fresh. Instead, new housing blocks were constructed in stages on available land, allowing families to relocate within the community as old units came down. That required intense coordination, not just in construction, but in utilities, access roads, and safety systems, all while keeping the neighborhood functioning. Before any new buildings could rise, the land itself had to be re-engineered. Jordan Downs sits on a former industrial site, contaminated from decades of adjacent manufacturing. That meant full environmental remediation, soil testing, removal of hazardous material, groundwater management, and installation of protective barriers. Engineers excavated tens of thousands of cubic yards of earth, replacing contaminated soil with engineered fill, compacted and monitored for stability. Next came infrastructure. The original Jordan Downs layout was a relic of mid-century planning. Isolated blocks with limited connectivity and almost no integration into the surrounding street grid. To fix that, the project involved installing an entirely new road network, complete with sidewalks, bike lanes, storm drains, and underground utilities. A major extension of Century Boulevard now runs through the site, connecting it to the broader Watts area and giving the community a direct arterial link to the rest of the city. Structurally, the new buildings are designed for both density and resilience. Wood frame over concrete podiums dominate the design, balancing cost efficiency with seismic durability. Each structure is engineered with fire suppression systems, earthquake-resistant framing, and energy-efficient insulation to meet California's Title 24 building codes. Sustainability was also baked in. Solar panels, drought-tolerant landscaping, and stormwater capture systems are integrated across the site. And unlike the original layout, the new Jordan Downs is being built with mixed-use development at its core. A central retail village is part of the plan, complete with grocery stores, cafes, and community-serving businesses. That required additional engineering for load-bearing slabs, commercial-grade ventilation, and enhanced utility access to support food service and retail operations. The project also includes new parkland, recreational facilities, and space for schools and job training centers, all of which had to be laid out on what was once a closed, fenced-off grid.
Rather than rising from untouched land, the new Miami-Dade Airport emerged through one of the largest continuous airport reconstruction programs ever undertaken in the United States, transforming Miami International Airport into what is effectively a rebuilt megastructure operating in real time. Miami International Airport sits west of downtown Miami and functions as the primary global aviation gateway for South Florida and Latin America. By the late 1990s, the airport's original mid-20th century terminals, roadways, and airfield systems were no longer capable of handling projected passenger growth, new aircraft sizes, or modern security requirements. Miami-Dade County responded by launching a long-term capital improvement effort, commonly referred to as the airport's New Airport Program, a reconstruction on the scale of a greenfield build while maintaining daily operations. The centerpiece of this transformation was the North Terminal Development Program, a multi-billion-dollar mega project that replaced large portions of the airport's aging infrastructure. Planning began in the late 1990s, with construction starting in the early 2000s. The program consolidated multiple older concourses into a single, linear terminal complex designed to improve passenger flow, security processing, and aircraft operations. Construction involved complete demolition of outdated concourses, utility corridors, and support buildings, followed by new foundations, structural frames, and terminal shells built adjacent to active runways and taxiways. This required phased construction sequencing to keep aircraft movements uninterrupted. New terminal structures were built using long-span steel and reinforced concrete systems capable of supporting large wide-body aircraft gates and high passenger volumes. The North Terminal was developed in multiple phases. Early phases focused on airside infrastructure, including new taxi lanes, aircraft parking aprons, and fuel hydrant systems. Subsequent phases delivered passenger processing spaces, including ticketing halls, security checkpoints, baggage handling systems, and customs facilities. The first major sections opened to passengers in the mid-2000s, with full substantial completion achieved in the early 2010s. A critical component of the new airport construction was the installation of an automated people mover system connecting the terminal to remote rental car facilities and parking structures. This required elevated guideways, stations integrated into terminal buildings, and control systems installed above active roadways. The people mover significantly reconfigured landside access to the airport. The reconstruction extended beyond terminals. Miami-Dade County invested heavily in runway rehabilitation and expansion, including pavement reconstruction, lighting upgrades, and drainage improvements. Taxiway geometry was modified to accommodate larger aircraft, such as the Airbus A380 and Boeing 777. These airfield works were completed incrementally over many years, often overnight, to avoid disrupting flight schedules. Cargo infrastructure was also rebuilt as part of the airport's mega-project evolution. New cargo buildings, cold storage facilities, and access roads were constructed to support Miami's role as a major freight hub for perishable goods. These upgrades aligned with parallel mega-projects at Port Miami, reinforcing the county's logistics network. Security and resilience upgrades formed another major construction layer. Post-9/11 requirements led to reinforced terminal layouts, expanded security screening zones, and hardened building systems. Mechanical, electrical, and plumbing systems were replaced or upgraded to modern standards, including redundant power supplies and advanced fire protection. Flood mitigation and drainage improvements were incorporated to address Miami's climate and storm exposure. The timeline of the new Miami-Dade Airport build spans more than a decade. major construction activity peaked between roughly 2004 and 2012, with continuous smaller projects extending beyond that period. By the early 2010s, the airport had effectively transitioned from a mid-century facility into a modern aviation megastructure, capable of handling tens of millions of passengers annually. Within the broader context of Miami's biggest mega projects, the airport reconstruction stands alongside developments such as the Port of Miami Tunnel, Brickell City Center, and large-scale transit investments. Unlike vertical mega projects, the airport rebuild was horizontal and systemic, requiring coordination across aviation operations, federal agencies, contractors, and airlines. Occupying the geographic and economic heart of Miami's financial district, Brickell City Center stands as one of the largest and most technically ambitious urban megaprojects ever constructed in South Florida. Brickell City Center is a multi-phase, mixed-use development spanning roughly 4 city blocks in the Brickell neighborhood. The project was conceived to redefine high-density urban construction in Miami by combining retail, office, residential, hospitality, and transit infrastructure within a single integrated footprint. Planning began in the late 2000s, with the formal development advancing in the early 2010s as Brickell rapidly transitioned from a low-rise banking district into a vertical urban core. Construction officially began around 2012, starting with extensive site preparation and demolition of existing structures. The scale of the project required a complete reconfiguration of underground utilities, including new water, sewer, electrical, and telecommunication systems capable of supporting millions of square feet of development. Deep excavation followed, with dewatering systems installed to manage Miami's high groundwater levels during foundation work. At the structural level, Brickell City Center required a complex system of reinforced concrete cores, transfer slabs, and podium structures. The development includes multiple residential towers, 2 major office towers, a hotel tower, and a large retail and entertainment podium. Each tower was built using high-strength concrete and deep pile foundations drilled into limestone bedrock to handle vertical loads and wind forces. One of the defining construction features of Brickell City Center is the climate ribbon, an elevated architectural canopy spanning the retail core. This structure required long-span steel framing and custom fabricated components designed to provide shade, ventilation, and rain protection in a subtropical climate. Installation of the climate ribbon occurred during the later stages of podium construction and required precise sequencing above active work zones. The retail podium itself was constructed as a multi-level structure occupying the center of the site. Large column-free interior spaces were achieved through the use of transfer beams and post-tension slabs. Mechanical and electrical systems were embedded within the podium to serve both retail tenants and the towers above, reducing redundancy and optimizing space. Office construction included 2 Class A towers designed to modern seismic, wind, and hurricane standards. These towers required curtain wall systems engineered for high wind resistance and solar control. Interior build-outs were completed after core and shell construction, with phased tenant occupancy beginning shortly after structural completion. Residential construction was delivered across several towers, each with distinct layouts but shared infrastructure systems. Vertical construction of these towers progressed concurrently, requiring careful coordination of cranes, concrete pours, and material logistics within a confined urban site. Residential units began delivering in phases starting in the mid-2010s. Hospitality construction included a high-rise hotel tower integrated into the overall podium. This required specialized structural and mechanical design, including back-of-house service zones, conference facilities, and rooftop amenities. Hotel construction was completed alongside residential phases to align with the overall project schedule. transit integration was a major component of Brickell City Centre's construction scope. The project directly connects to the Metro Mover system, requiring new station interfaces, elevated walkways, and structural modifications to existing transit infrastructure. These connections were built while the Metro Mover remained operational, adding complexity to sequencing and safety planning. The construction timeline unfolded in defined phases. Major vertical construction occurred between approximately 2013 and 2015. The retail component of Brickell City Centre opened in late 2016, marking a key milestone for the project. Office and residential towers reached substantial completion around the same period, with additional residential deliveries extending into 2017. From a mega project perspective, Brickell City Centre was notable for its centralised construction management and financing structure, allowing multiple buildings to rise simultaneously rather than sequentially. This approach shortened the overall development timeline, but increased coordination demands across trades and contractors.
The Metro Regional Connector is just 1.9 miles long, but its impact ripples across the entire Los Angeles basin. Beneath the chaotic sprawl of downtown, this subterranean link has silently transformed the backbone of the city's transit network. Not with flashy architecture or sweeping overpasses, but with precision tunneling and deep engineering ambition. It's a mega project built not to be seen, but to be felt, every time a train glides through the city uninterrupted. Before this connector existed, Los Angeles had a problem. Its growing light rail system, the A, E, and L lines, stopped short of being truly regional. Trains terminated downtown, forcing commuters to transfer between lines, often in disconnected stations, wasting time and discouraging use. The system worked technically, but it didn't flow. It didn't breathe. The regional connector changed that. By boring two parallel tunnels through the dense urban core and tying together these once isolated lines, it created the first true one-seat ride across the county. Now a passenger can board in Azusa and ride directly to Long Beach. East Los Angeles to Santa Monica, no transfers, no transfer platforms, just a straight shot through the city's heart. It's a small piece of track, but a massive leap in connectivity. But connecting three major lines under a century-old city is anything but simple. Downtown LA is layered in complexity, filled with pre-existing tunnels, water mains, sewers, building foundations, earthquake faults, and a living, breathing population above. To carve a clean path through all of it, engineers had to think in three dimensions, navigating not just forward, but over, under, and around everything in their way. The answer came in the form of two tunnel boring machines, Angeli and Elsie. Each one was a 1,000-ton beast, stretching over 400 feet long, with rotating cutter heads capable of grinding through soil, rock, and buried urban history. But the real trick wasn't speed, it was control. Tunneling through this part of LA meant passing just feet beneath sensitive structures like the historic Broadway corridor and active subway lines, where even the slightest misalignment could cause cracks or settlement. So crews worked slowly, methodically. Pressurized faces on the TBMs stabilized the ground ahead. Real-time monitoring systems tracked every vibration and movement, sending feedback to operators above. In some segments, the margin for error was less than an inch. It was engineering done with surgical precision, buried beneath a city that never stopped moving. At the surface, the work was just as intense. 3 brand new underground stations were constructed. Little Tokyo Arts District, Historic Broadway, and Grand Avenue Arts, Bunker Hill. Each of them had to be excavated in tight quarters, often amid live traffic, aging buildings, and pedestrian zones. the Little Tokyo station posed one of the greatest challenges. Crews had to demolish the existing above-ground station, reroute the tracks underground, and do it all while preserving the cultural heart of a vibrant neighborhood.
Rising from the western edge of downtown Miami, Panorama Tower represents one of the most consequential vertical construction efforts in the city's modern history and stands as a defining chapter in Miami's era of megaproject development. Panorama Tower is an 85-story, mixed-use skyscraper located at 1101 Brickell Avenue, positioned at the intersection of Brickell downtown and the Miami Health District. When it topped out, it became the tallest building in Florida, reaching a structural height of approximately 868 feet. Construction began in 2013, and the tower was officially completed in 2018, following a multi-year development cycle that coincided with Miami's rapid transformation into a global high-rise city. The project was developed by Florida East Coast Realty, a company with deep historical ties to the state's infrastructure and urban development. Panorama Tower was conceived not as a single-purpose building, but as a vertically integrated megastructure combining residential, office, hotel, and retail space within one footprint. This approach reflected a broader shift in Miami construction during the 2010s, where land constraints and economic growth pushed developers toward dense, mixed-use, vertical solutions. The construction scope of Panorama Tower was extensive and technically demanding. The tower contains more than 2.8 million square feet of total built area. Its program includes approximately 821 residential units, over 200,000 square feet of Class A office space, a 208-room hotel, and significant ground-level retail and parking infrastructure. The building's foundation required deep piling systems designed to anchor the structure into Miami's limestone bedrock, a critical engineering challenge given the city's high water table and coastal soil conditions. Structurally, Panorama Tower uses a reinforced concrete core and shear wall system, a method commonly employed in super tall residential towers, but executed here at unprecedented scale for Florida. High-strength concrete mixers were required to handle vertical loads at extreme heights, and the construction sequence demanded precise coordination to maintain schedule while pouring floor plates at increasing elevations. Wind engineering played a central role in the design, with the tower engineered to withstand hurricane-force wind loads common to South Florida. Construction logistics were particularly complex due to the site's proximity to major roadways and active urban districts. Crane operations, concrete deliveries, and vertical material transport had to be tightly managed to minimize disruption to surrounding neighborhoods. At peak construction, hundreds of workers were on site daily, contributing to one of the largest active construction projects in Miami at the time. The timeline of Panorama Tower closely mirrors Miami's broader construction boom. Groundwork and foundation activities began shortly after the 2013 groundbreaking. Vertical construction accelerated between 2015 and 2017, during which the tower surpassed all other buildings in the state in height. Topping out occurred in late 2017, marking a symbolic milestone for Miami's skyline. Interior build-out, systems commissioning, and phased occupancy continued into 2018, when the project reached full completion. Within the context of Miami's megaproject landscape, Panorama Tower stands alongside developments such as Brickell City Center, Miami World Center, and the ongoing expansion of the downtown and Brickell corridors. Unlike large multi-block projects, Panorama Tower condensed megaproject scale into a single vertical structure, demonstrating how Miami's growth could be achieved upward rather than outward. The building also marked a shift in how Miami approached mixed-use density. By stacking residential, hospitality, and commercial uses, Panorama Tower reduced reliance on horizontal sprawl and car-dependent layouts. Its parking systems, mechanical floors, and vertical circulation were engineered to support thousands of daily occupants within a single building envelope.
Brightline West isn't an idea, it's under construction. A $12 billion high-speed rail megaproject designed to link Los Angeles to Las Vegas in just over 2 hours, cutting a trip that often takes over 5 by car. With speeds reaching 200 miles per hour and over 260 miles of new rail corridor, this is one of the largest and most complex infrastructure projects ever attempted in the American Southwest. The alignment runs primarily along the I-15 corridor, chosen for its straight path, existing right-of-way, and the massive volume of traffic it sees. Over 50 million people travel between LA and Las Vegas each year, many of them stuck in stop-and-go congestion. Building next to a major interstate, however, comes with logistical and engineering demands on a different scale. Crews must work within narrow margins between freeway traffic and construction zones, requiring extensive concrete barriers, temporary detours, and phased sequencing to avoid bottlenecks. The trains will operate entirely on dedicated, grade-separated track. That means no level crossings, no signal delays, and no sharing with freight or commuter rail, making Brightline West a true high-speed rail system by global standards. To achieve this, over 300 structures are being constructed along the route, including overpasses, bridges, wildlife crossings, and viaducts. Every one of them is engineered to withstand extreme desert heat, high wind speeds, and seismic loads consistent with California building codes. One of the most technically demanding sections involves crossing the Kaijon Pass, an elevation climb of over 3,000 feet between the Inland Empire and the high desert. This stretch requires extensive cut-and-fill operations, retaining walls and reinforced embankments. Specialized track design, including banked curves and controlled gradients, ensures that trains maintain high speeds without overstressing the vehicles or the infrastructure. Trackbed construction is another layer of complexity. Unlike conventional rail, high-speed systems require exacting tolerances for smoothness and alignment. The subgrade must be compacted and stabilized to millimeter-level accuracy, followed by multiple layers of ballast, reinforced concrete slab track, and vibration-damping materials. These systems are monitored in real time through embedded sensors, allowing for predictive maintenance and immediate response to deviations. Powering the system is an electrified catenary line running the full length of the corridor. This requires constructing hundreds of miles of new transmission infrastructure, including substations, overhead gantries, and high-voltage feeds. To ensure uninterrupted service, the power supply is designed with built-in redundancy and real-time switching capabilities. Utility coordination across 2 states and multiple counties adds further layers of complexity to every mile built. The train sets themselves, based on Siemens Velaro or similar European high-speed rail platforms, will be custom-modified for American standards. Each unit will feature aerodynamic nose cones, regenerative braking systems, crash energy management structures, and lightweight aluminum bodies to reduce axle load and track wear. These aren't commuter trains. They're precision-built machines designed to run at 200 mph across open terrain, with acceleration, deceleration, and safety systems modeled after Japan's Shinkansen and Germany's ICE,